Yes, good morning.
Morning.
Good morning.
All right, thanks. Welcome to the second day of ESIAM 21. It's been an exciting and quite intense first day. And today we just want to continue with that. Thank you so far for your great contributions and for your scientific discussion. I'm the chairman of the first session today, so I have the honor to welcome to the stage Matteo Benedetti and Armin Wiedenecker. So both speakers are kind of reflecting the scientific world and also the industrial world. So you can see where we want to go today. We want to talk a little bit also about applications in the next session in aerospace and lightweight design, and also in biomedical applications, until we going to start again with an intense session in the afternoon of fatigue of AM metals. But first of all, I want to introduce myself. I'm Jan Torgersen. I'm professor for mechanical engineering at NTNU Trondheim, a colleague of Filippo Berto, and we one of the organizers of this conference. So I think that we are 32 participants now, so we could just welcome Matteo to the stage. Maybe Matteo, you can talk a little bit briefly of what your role is in the University of Trento.
Okay.
And before you start with your exciting talk about fatigue of architectured cellular materials.
So actually my presentation, I'm going now to share introduces myself as well. So good morning to everybody. First, I'd like to thank the organizing committee of this very nice conference for inviting me to give this plenary lecture, particularly my dear friend Filippo Berto. My name is Matteo Benedetti. I'm an associate professor in machine design at the University of Trento in Italy. So very likely, very few of you know where Trento is. So I'd like to spend a few words to present Trento and its university. Trento is a medium city located in the middle between Venice and Milan, in the middle of the Italian Alps, approximately near Garda Lake and the Dolomites. Trento hosts a relatively young, medium-sized university, yet rated among the best Italian universities in a good position in international rankings. So I belong to the Department of Industrial Engineering, recently nominated Department of Excellence by the Italian Ministry for Universities. Here is an example of the department research infrastructures in which I'm mainly involved. I focus on the mechanical characterization of structural materials and also in numerical modeling of products and processes. So we are fully open to international cooperation, so also in the form of EU projects and staff exchange. So it would be nice to have you visit here. So now I come to the subject of my talk. This will be focused on additive manufacturing of architected cellular materials, with particular attention to the role of manufacturing on the mechanical properties, especially fatigue, and also dedicated to design and technological measures aimed at improving their structural integrity. So materials occurring in nature are often characterized by a complex multi-scale hierarchical porous architecture. On the left, we can see here the microstructure of bone, consisting of a thin, solid layer of cortical bony tissue attached to a highly porous cellular core of cancellous bony tissue. On the right, a natural hexagonal honeycomb is compared with a metallic honeycomb structure widely used in aeronautic context. So basically, taking inspiration from nature, a new class of engineering materials is gaining more and more interest in the academic and industrial field, generically termed as architected metamaterials or cellular materials. In the very commonly investigated strut-based lattices, nodes located at the vertices or edges of unit cells are linked by slender members, usually termed as struts. Besides strat-based lattices, other architected cellular materials that are gaining increasing interest are based on triplet periodic minimal surfaces, TPMS. So TPMS are surfaces created mathematically such that have a zero mean curvature at each point. My talk, will be focused on strat-based lattices. My dear friend, Professor Duplessis, will give a plenary lecture about fatigue strength of TPMS gyro structures. So cellular materials find nowadays disparate applications. Here we can see a diesel piston, a fluid pump, racing car cylinders, brackets, in all cases to reduce the mass of structure while fulfilling mechanical performance requirements. But also they are used for thermal management, as in heat sinks and heat exchangers. But the industrial branch that is now readier to employ cellular metamaterials is for sure the biomedical implant sector. The reason resides in the necessity of ensuring long-term implant stability by reducing stress shielding due to stiffness mismatch between implant and body tissue. Here we see the flow chart of the design methodology designed by Canotti and Pezzini at McGill University, Canada, in which multi-scale mechanics and design optimization are used to synthesize a graded lattice implants with simultaneously reduced stress shielding and implant interface failure. So it is now clear that the most appealing property of cellular metamaterials is that their microarchitecture and their relative density can be modulated to confer to the component the desired properties. To this regard, closed form equations were proposed by Gibson and Ashby to express elastic modulus and also yield strength as a function of the relative density. They assume that the cell strat behave like slender and straight Euler-Bernoulli beams. Importantly, different equations were derived depending on the stretch or bending dominated behavior of the unit cell type, or equivalently on the sign of the M coefficient of the Maxwell stability criterion. The Ashby equations are able to capture most of the trends displayed by experimental data as a function of the relative density. Interestingly, the majority of experimental data is in better agreement with the Gibson-Ashby prediction for bending dominated behavior, even though some of these cell architectures were nominally classified as stretch dominated. As we will see in more detail later, this experimental evidence is due to geometric inaccuracies, which can strongly affect additively manufactured cellular materials. In contrast to elastic modulus and static strength, which are representative of the global response of the lattice materials, there are other mechanical properties that are dictated by the material response at the local scale. One of them is the fatigue strength, which represents the resistance against time-varying loads. The fatigue behavior of cellular lattice materials is of great concern, as these materials are particularly prone to fatigue damage because their microarchitecture is an intrinsic factor of structural weakening, since a full geometry is replaced by a porous structure consisting of struts joined at particular points termed nodes, reducing the load-bearing area and increasing stress concentrations. These materials are produced via additive manufacturing, and we know that AM products are often characterized by geometric imperfections, we can see here, surface irregularities, internal pores, which leads to differences between the as-built and the as-designed part. There are technological limitations that pose lower limits on the size of the minimum printable geometrical details, such as the strut thickness. In a nutshell, fatigue, more than any other mechanical property, is strongly affected by the manufacturing process. So as a result, there is still a widespread concern about the structural integrity of these materials, especially under fatigue loading. The main issue is in the study of the fatigue behavior of these materials is that no standards are available for the mechanical testing. The only available standard is the ISO 13314, which prescribes a procedure for the monotonic compression testing of metallic random forms that exhibit a ductile plateau behavior. The main prescription is about the minimum number of 10 cells along the diameter to ensure sufficiently low sensitivity of the results to the edge effects. This requirement has been verified to work well also for periodic cellular materials, when global mechanical properties like elastic modulus and compressive strength must be determined. In fact, such mechanical properties display a convergent behavior above 5-6 unit cells. However, no systematic investigations were done on the minimum number of cells necessary for fatigue tests to be sufficiently less sensitive to edge effects. Since fatigue is a local phenomenon, I expect that fatigue strength is much more sensitive to edge effects, and this crucial aspect must be faced when designing standards for fatigue testing of cellular materials. So anyway, a certain amount of experimental data was published so far in the literature, almost uniquely for compression fatigue. This chart summarizes data we extracted from a literature survey in terms of fatigue strength normalized by the yield strength as a function of the open porosity, which is the complement one of the relative density. Even though the fatigue strength are normalized with respect to the corresponding yield strength, the data still display a decreasing trend with increasing porosity. So this demonstrates that the reduction in fatigue strength with increasing porosity is more pronounced than that in yield strength. So fatigue, as we know, is a local phenomenon, very different from yielding that affects the global mechanical response of the entire porous material. Therefore, the yield strength is not able to capture the entire detrimental effect exerted by porosity on the high cycle fatigue strength. So considering that bulk structural metals display typically a normalized fatigue strength above 0.5, it can be observed that very few cell architecture and materials achieve similar performances, notably truncated cubo-octahedron, rhombic dodecahedron, TPMS gyros, cell architectures, and very ductile metals like cobalt chromium alloys. So in more recent literature, there has been a growing awareness that a better understanding of the fatigue behavior of cellular materials would be achieved if the experimental fatigue characterization were also conducted under global tensile stresses. This, however, poses a considerable experimental challenge as the specimen geometry must be designed to make possible the transfer of tensile loading from the machine to the sample and to locate specimen failure in the sample central gauge part, where edge effect must be minimized. So this figure reviews some of the specimen geometry proposed in the literature to test cellular materials under tensile fatigue load. The more disparate geometries has been proposed so far, in general involving very few cells along the transversal direction. Therefore, we expect the results to be affected by side effects. So this kind of specimen geometry makes possible the determination of the high diagram that expresses the effect of the mean stress on the fatigue strength. The experiments reported in this chart show a negligible effect of the load ratio in the compression regime only. On the other hand, the application of positive tensile mean stresses reduces considerably the fatigue strength, especially for the sheet gyro specimens. So to permit the application of tensile global stressing and at the same time to accommodate a larger number of cells in the transversal direction, we are now devising in our university a specimen geometry here illustrated in this figure adopting both the flanges as mechanical interfaces to the test machine. The solid members are, as you see here, bell-shaped. To make the load transfer from the bolt to the central porous part of the specimen more uniform. We have already successfully carried out some fatigue tests whose results will be shown later, and we will be very happy to collaborate with anyone of you to explore the tensile fatigue strength of various cell architecture and to come to the definition of a standardized specimen geometry. So we have seen so far that design porosity and cell architecture play an important role in fatigue performance of cellular materials. There are, however, other factors affecting the fatigue strength of these materials, essentially related to the additive manufacturing process used to fabricate them. To this regard, we can observe from this CT scan of a single strap irregular surface morphology, attach unmelted particles impacting on the effective cross-section shape and cross-section diameter, and also altering the stress field as shown in this final element simulation. So these stress hotspots are in general site of preferential fatigue crack initiation, as can be seen in this micrograph taken from a fatigue strut-based lattice material. So in addition to surface roughness, there can be a considerable deviation between the as-designed geometry and the as-built geometry. And this issue is in particular relevant in parts with fine details, such as cellular lattices. The accuracy of laser-based additive manufacturing processes is determined by the size of the melt pool. The bigger it is, the more difficult it becomes to reproduce fine details. In the case of lattice materials, the size of the melt pool depends also on the strut orientation. So heat is carried away more efficiently by vertical struts than by horizontal struts. So they display improved surface appearance and geometrical accuracy compared to horizontal struts. In general, we observe accumulation of parasitic material below the strut with respect to the printing direction. The main fatigue-related consequence is that if the nodes are intentionally filleted to reduce the stress concentration, the beneficial effect of this design measure is diminished by the reduction in the actual fillet radius in the down-facing surface of the node. So to assess the impact of the printing direction on the fatigue strength of single struts, we recently manufactured miniaturized fatigue specimens in which the gauge part mimics a single strut of about 600 micron diameter. Samples were printed along different building direction and tested under reverse axial loading. The strut cross-section progressively deviates from the circular one with reducing printing angle, and at the same, we see that with reducing building angle, the roughness increases, especially in the downskin part of the strut. So this results in a dramatic reduction in the fatigue strength of the struts inclined less than 45 degrees, 15 and 0 in this case. To confirm the crucial role exerted by the irregular surface morphology, fractographic analysis attested crack initiation from surface notches and little influence exerted by internal porosity. So this evidence is confirmed by many investigations published in the literature. So to our knowledge, only one paper attested superficial crack initiation from internal porosity. In the remaining works, the fatigue damage started from surface defects located in the vicinity of nodes, in location where the stress concentration concomitantly produced by the lattice node and surface notches is highest. So it is therefore clear that if we want to increase the fatigue strength of these materials, the surface must be modified by a suitable treatment. In the chart in the center, we reported the fatigue strength increment of titanium 6-4 diamond lattices with respect to the as-built condition produced by different treatment. So importantly, hyping results in a fatigue strength increment comparable to that of a simple super beta transfuse heat treatment, demonstrated that hyping alone is beneficial only because we modify the microstructure through the thermal treatment and not because we close internal porosity. So the fatigue damage in this case is still controlled by surface irregularities. So if we want to fully exploit the benefits of hyping, we must combine hyping with a surface conditioning treatment like sandblasting or chemical etching to attenuate the detrimental effect of surface defects and the presence of brittle alpha case generated during hyping. So if we want to further improve the fatigue strength by attenuating the stress concentration at the junction between the struts, we need to eliminate the associated geometrical discontinuity. So the group of Professor Savio in Padua University, Italy, investigated 3 different node topologies at the intersection among circular struts. So a non-filleted node, a node with conventional fillet, and a node with a continuous shape variation ensuring continuity in tangent and curvature. So the enhancement in fatigue strength of the filleted variants is evident from this chart, summarizing the results of fatigue tests carried out on lattice specimen made of polymeric materials. So the further investigate possible design measures to improve the fatigue strength, we carry out an experimental campaign employing the specimen with threaded flanges interface shown before. Specifically, we tested 4 batches of samples, all of them characterized by a cubic unit cell of 4 mm, filleted nodes, and axial load applied parallel to the printing direction. And this batch was compared with other batches, B, D, and E, which are characterized by a printing direction rotated by 90 degrees, the absence of filleted nodes, or a reduced unit cell size of 3 mm. So the resulting SN curves are here compared in terms of homogeneous axial stress, where a marked beneficial effect of introducing filleted node is evident. So the high cycle fatigue strength is improved by a factor 2. On the contrary, a rotation by a 90 degrees angle in the printing direction causes the strut printed parallel to the printing direction to carry the axial load with a dramatic reduction in the fatigue strength. Due to the poor geometrical accuracy we have already seen in the miniaturized specimens. Interestingly, the unit cell size reduced to 3 mm doesn't significantly alter the fatigue strength. However, if we add in this chart plotting the normalized high cycle fatigue strength versus the cubic unit cell size, also, normalized to the yield strength versus the unit cell size, also the results of fatigue tests done on samples with 1.5 mm unit cell size, we can see that increasing the cell size from 1.5 to 3 mm results in improvement in the manufacturing accuracy of the lattice and consequently in a significant fatigue strength enhancement of a factor about 2, and then the fatigue strength tends to remain constant for larger unit cell sizes. Moreover, if we enrich this scenario with the outcomes of ongoing investigations we are conducting on the same cell architecture, but made of a novel beta titanium alloys, we can observe that the stress concentration factor evaluate the important CP scans of the real geometry into a FE simulation remarkably increases in a similar fashion for lattices made of both materials for unit cells sizes smaller than 2 mm. So we can argue the existence of a manufacturability threshold in the unit cell size below which the fatigue properties decline considerably. From the investigation shown here, it seems that printing metamaterials with open porosity smaller than 2 mm results in poor fatigue properties and should be avoided. This, however, might have an important consequence in the design of architected materials for biomedical implants. In this case, the cell architecture must not only satisfy structural integrity requirements, but also biological osseointegration requirements for a proper bone-in growth into the implanted cellular material. So in the technical literature, it is commonly accepted that open porosity must be comprised between 0.3 and 0.6 millimeter for osseointegration, thus much smaller than the manufacturing threshold of 2 millimeter we have found before. So to relax these conflicting requirements, we are now working on the design of a novel porous end plate of a spinal cage implant, where the basic idea is to decouple the structural and osseointegration functions. For this purpose, a large-sized primary cellular structure is designed only to withstand mechanical load, while a secondary finer cellular structure is incorporated into the primary one to fulfill biological requirements. More specifically, I'm collaborating with a colleague in biomaterials engineering on the fabrication of architected multi-materials wherein the metallic load-bearing structure is filled through electrowetting with a polymeric osseointegrative foam made of silk fibrin and gelatin. So the adhesion pull-off test and ESIAM analysis demonstrated the capacity of the foam to remain adhered to the metallic cage during the application of the mechanical load. The identification of the manufacturing threshold we have seen before required the fabrication of very large specimens. The quantity of specimen necessary to build a single SN curve occupied a whole job of a Renishaw AM250 machine. So to make the conduction of such fatigue investigation faster and cheaper, we are now evaluating the possibility of carrying out fatigue experiments on miniaturized specimens, mimicking a single filleted node of the macroscopic structure in which 4 struts are converging. Field radius and strut thickness are nominally the same as those of the macroscopic samples. Moreover, we tested samples along different building directions. So the resulting SN curve are here compared with those obtained using the specimen counterparts without central node, shown in dashed lines. So the reduction in fatigue strength is produced by the stress concentration of the node is particularly evident for the samples printed along the 90 degrees direction. Those printed along the 0 degrees direction are less sensitive to the presence of the node because they are already weakened by the irregular surface morphology. Interestingly, if we compare the SN curve of batch A of macroscopic specimens here with flanged mechanical interface with that of miniaturized samples printed along the same direction, a good agreement is obtained between 10 to the 5 and 10 to the 6 cycles, whereas the miniaturized specimens tend to underestimate the fatigue of the macroscopic specimen in the high cycle fatigue regime. The discrepancy can be in part explained invoking the fact that more than one strut must break under fatigue in the macroscopic specimen before the complete failure of the macroscopic specimen. So an interesting aspect we found when analyzing the CT scans of additively manufacturing lattices is the significant deviation of the real geometry from the nominal one. In general, the strut thickness tends to be oversized with respect to the desired value, making the real mechanical properties, especially stiffness, very different from the expected ones. So here we see an example of cubic lattice monotonically tested under tensile loading. CT scans revealed a broad distribution in strut thickness, where the mean is about 50% higher than the nominal value. If a FE model is built to predict the mechanical properties of the lattice structure, a much better agreement of the stress strain curve is obtained when the FE model is built considering the CT reconstruction instead of the CAD geometry. So these considerations hold true not only for strut thickness, but also for other geometrical details, like the radius of filleted nodes. Here you see the main outcomes of the metrological characterization we made on miniaturized single node specimens I showed before. So it can be noted that the deviation of the field radius from the S design value depends on the inclination of the sample with respect to the building plane, but also on the location of the fillet with respect to the longitudinal axis of the specimen. It can be noted that the accumulation of parasitic mass in the underskin location 3 makes the fillet radius larger at the expense of the fillet located in the upper skin at location 2. So it is therefore clear that if we want to make the mechanical properties of architected cellular materials more controllable and predictable, the systematic deviation in geometrical parameters must be eliminated, or at least reduced through a suitable back compensation strategy, whose theoretical framework is here summarized. So one of the main sources of geometrical inaccuracies have been identified. A metrological characterization of S-printed structure must be performed. The obtained results are elaborated so as to differentiate the deviation of each geometrical parameter according to the orientation with respect to the printing direction. Then a relationship between the S-design and the S-build parameter is established, and this relationship is used to generate a compensated CAD model of the desired structure to be printed. So we are currently attempting to apply these theoretical frameworks to the compensation of the strut thickness. It can be noted that the relationship between S-design and S-build strut thickness is well represented by a linear expression, and this expression depends on the inclination of the struts with respect to the building direction. After compensation, the mismatch of the strut thickness from the CAD value is dramatically reduced as to compare to the non-compensated strut. So we are now trying to apply the same idea to the compensation of the fillet radius, a prototype of node in which each fillet surface is compensated differently according to its location with respect to the specimen axis was generated and is now under fabrication. So the dependency we observed of the fatigue strength of strut orientation with respect to the building angle suggested the idea that instead of fabricating cellular materials where each unit cell has struts of identical nominal thickness, it would be preferable to adapt the thickness of each strut to the local loading conditions so as to maximize the fatigue strength. So this approach is also useful to identify the orientation of a product in the building chamber to optimize its fatigue strength. For this purpose, we have implemented this relationship, fatigue strength versus strut orientation angle, into an optimization algorithm in which the objective function is to maximize the minimum safety factor of the structure, of the wicked strut, and an equality constraint is introduced in order to fulfill a requirement in compliance, for instance, to avoid stress shielding issues in implants. So here you see a simplified two-dimensional lattice structure loaded under 3-point bending and discretized with stretching dominated unit cells. So we can observe that after optimization, each strut is characterized by a different cross-section area shown in color scale, depending on the location and orientation of the strut. The safety factor against failure is well above the unity in all the struts. Moreover, if we introduce the orientation of the struts in the building chamber as an additional design variable, we can observe that the safety factor is increased when building angle is changed from 90 degrees to 60 degrees. So we are now trying to extend this approach to three-dimensional lattices. Here we see the same beam under 3-point bending, discretized with stretching dominated octet truss unit cells, in which we assign different thicknesses to each strut. We plan to print soon prototypes to make sure that this optimization approach results in an enhancement of the fatigue strength. So now we have come to basically the end of this lecture. I'd like to summarize the main issues in the fatigue behavior of cellular lattice materials. So an extensive and reliable fatigue testing is necessary for a deep comprehension of all the fatigue-related issues. For this purpose, miniaturized specimens are of particular interest because they permit to build low-cost experimental batches and to mimic geometrical features at sub-millimeter scale. There is a strong demand of standardized testing geometries and protocols to perform repeatable and reproducible fatigue experiments. This concerns fatigue testing under tensile loading and under multi-axial loading. The complex interplay between internal porosity and surface imperfections and nodes geometry needs to be further investigated. Environmental effects on the fatigue behavior of cellular materials are till now an explored field of investigation, yet of paramount importance if we think at the aggressive human body environment, very different from the laboratory in which fatigue tests are usually done. To this regard, we are designing and fabricating a suitable chamber to conduct fatigue tests on miniaturized specimens in body simulated environment. Architected cellular materials naturally lend themselves to be structurally optimized, but in doing so, crucial aspects must be considered, such as manufacturing constraints on the minimum printable geometrical details to achieve adequate fatigue strength, the necessity of compensating systematic manufacturing errors to make the mechanical properties more predictable, incorporating the effect of building direction on the fatigue strength, and providing nodes with fillet to attenuate stress concentration. Adapting the cross-section size of the strut to the local loading conditions and the specific orientation depending fatigue characteristics. Devising efficient design approaches of the interface of cellular polymer materials with fully solid bulk interface, like those shown for axial fatigue loading. Last but not least, we shall not forget the important role played by the base material used to fabricate cellular materials. So therefore, we need to design new metallic alloys specific for additive manufacturing, for instance, beta titanium alloys for biomedical application. Take advantage of anisotrope introduced by process instead of simply eliminating it with a heat treatment. Combine efficiently thermomechanical treatment to improve concomitantly surface morphology and internal porosity. And finally, devising multi-materials to fulfill conflicting requirements like structural integrity and osseointegration. So before closing my presentation, I would like to express my deep gratitude to my research group composed of young and enthusiastic researchers, and to extend it also to all the people around the world whom I have the privilege to collaborate with. I acknowledge also the fundamental support of Lincotech Medical that fabricated most of the samples employed in the investigations shown in this presentation. Here you see a list of the main publications that gave inspiration to this talk. So thank you so much for your attention.
Thank you very much, Matteo, for this very nice talk and very deep insight into cellular materials on the dynamic loading. I'm sure that there are some questions regarding Matteo's talk. You can also use the chat or just unmute.
Thanks so much.
So people are a bit hesitant right now, but I would like to kickstart the discussion, and I would like you to comment on the fixture you were using, because you showed various types of transition between the cellular material and the fixture of your specimen that goes into it. So there are different ones. You once showed one with a curvature, and once you showed some with a kind of a porosity gradient. Can you tell us a little bit about your experience, what works and what works not?
I share again my screen and I go back to the slide showing this geometry. Okay, on the left, you see the first conceptual idea. So an idea of a sample that can accommodate a larger number of cells, resulting in a gauge diameter much higher than the typical diameter for mechanical interface to testing machine. And so in order to accommodate this mismatch, we thought about the idea of a bolted flange. A bolted flange has the advantage that you can, after printing, rework the samples by milling in order to ensure the parallelism between the two plates that act as interface to the testing machine. In this case, you can minimize the spurious bending effects that arise from distortions related to the printing of the sample. So this was our idea, because in our first prototypes, this was made directly by additive manufacturing. This was a unique piece, but what we realized that there is a misalignment here in the two threaded ends that introduces spurious bending effects when mounting onto the machine. And then we have the problem, however, that the lines of the flow or line of forces has a complicated path. So it goes from the ends, passes through the bolts, and then enters into the sample. In general, this results in a non-uniform distribution of the axial stress, as you can see here. So in general, the central part is unloaded with respect to the outer part. In order to make more homogeneous the stress distribution in the cross-section, we came to the idea of a bolted flange with a non-uniform thickness, having this bolted flange, bell shape. In this case, this gradient in stiffness makes possible a more uniform distribution of the action. Then we have the problem that we don't want to have fatigue failure in the transition zone. And so here we have basically a density gradient going in this direction, in the axial direction, to make thicker the struts in this region, and to avoid, in this case, the fatigue failure at the transition with the bolted flange. And we are able to basically locate in any test the fatigue failure in the central cellular zone with the uniform porosity.
Okay, thank you very much for this insight. Are there any other questions?
Hello, I have a quick question.
May I? Sarah.
Hi, Matteo. Thank you very much for the very comprehensive overview that you gave on the fatigue of cellular structures. My comment was on cell-phase state. As you mentioned, it's a huge issue still in the fatigue properties of cellular structures. And I was wondering, considering that most of the cell-phase treatments that are commonly used for additive manufacturing are line-of-sight treatments, probably apart from chemical etching or chemical, let's say, treatments. I was just curious to know your experience about that, whether you find, let's say, some other treatments with higher potential for cellular structures.
I have some experience in post-fabrication treatments, mainly on bulk specimens. And so, as you know, high pin and chemical etching have beneficial effects, the former because you close porosity and you modify favorably the microstructure, the latter you remove a surface roughness, which is critical in fatigue behavior of bulk specimens. For cellular specimens, the application of post-fabrication treatment is much more delicate for several reasons. On one hand, talking with let's say orthopedic experts, there is the idea that a post-fabricated surface, so with a very irregular surface, should be beneficial for the osseointegration because it stimulates the ingrowth of the bony cells. And so there is some mistrust against chemical etching or sandblasting procedure that basically makes this surface morphology smoother. And another issues regard hyping. So hyping is another very delicate process, especially for titanium alloys, because as far as you know, it's not possible to perform hyping under vacuum conditions. So we are forced to do hyping in a protective argon environment, inevitably contaminated with oxygen. And as you know, titanium is very reactive against the oxygen. And this results in the formation of a brittle alpha layer that is very detrimental to the fatigue strength. So if you are building bulk specimens, this is not particularly an issue because you can remove by grinding the alpha layer and you can restore the full fatigue properties of the material. But in the case of cellular lattice materials, which we have very, very thin struts, eliminating the brittle alpha layer is not so easy. And so you must be very, very careful in not removing too much material, for instance.
Good, thank you.
Thank you. So I don't know who was next, maybe Guyan?
Yeah, thank you very much, Mata, for your very interesting talk. So I have a question. Yeah, concerning this cellular material, also this lattice material, I think for me it's more like it's a kind of structure compared to this very small specimen, which is used generally for the fatigue test or tensile test. So it's more or less is more the structure. So for this structure, I think for the fatigue test or tensile test, I think we can also design the structure, and then there will be quite a lot of discontinuous locations. And then in this sense, the intrinsic defect due to additive manufacturing, such as the porosity, lack of fusions, this effect may not be so detrimental compared to the small specimen, because for this specimen, they are quite more uniform, but for this cellular structure, they can be a lot of more discontinuous. So this kind of intrinsic defects could not be so detrimental. So I think maybe you can also comment a little bit on this aspect.
Yes, I agree with you. So lattice can be defined better as structure as material. I agree with you. And so a fatigue design must include also the interface of the structure to the rest of the component. So in this sense, I think miniaturized specimen can be of great help because we can determine the fatigue strength of the single strut depending on the orientation. And then we must incorporate this information into the design of a structure composed of many struts, nodes, and also of interface and complex boundary conditions. And regarding the effect of porosity, so I also agree with you because as far as I know, and also based on my experience, internal porosity in very thin struts is not of so much detrimental effect. So what is dominating is the stress concentration of the nodes, and what is also dominating are surface irregularities. So in general, internal porosity plays an important role only after removing the stress concentration effect produced by nodes and also by surface irregularity. So only in this case, it makes sense to eliminate internal porosity.
Yeah, so I think there will be a kind of a crack initiation competition. That means a competition between stress concentration and porosity, like fusions. So
yes, I agree.
Which factor will prevail or will dominate? Yeah, thank you.
You're welcome. Thank you.
Yeah.
So Anton, a very short question.
Yes, I have a very quick question. I know we're running out of time. Very good presentation, Matteo. Thank you very much.
Thank you, Anton.
Excellent. I was interested about the tensile failure modes, if they correspond to compression failure modes. For example, for you find diagonal failure versus layer by layer failure in compression testing. If this for bending and stretch dominated mode structures, is this the same in tensile, or can you comment on this?
Yes, as you know, tensile stresses are much more detrimental than compressive stresses in producing fatigue damage, especially because you tend to open in mode 1 the crack after initiation, and you facilitate its propagation. So the difference between compression and tension test depends basically on the cell architecture, in my opinion. So if the cells are composed of bending dominated unit cells, so there is a part of the cross section of each strat which, due to bending stresses, is under global tensile stresses, and here you see a tensile mode of fracture. In case of, for instance, cubic cells, in which we have struts oriented exactly along the load direction. So in this case, the load is borne by these struts. These struts are basically loaded under almost uniform compression stress state. And in this case, we see a very different fracture morphology that is not so easy to recognize, because you have a huge smearing of the crack faces due to the contact produced by the compressive stresses. And it's very, very difficult to determine the defect triggering the fatigue initiation crack under pure compression test.
Okay, thanks.
You're welcome. Thank you, Anton, for asking.
Okay, then I will close this talk. Thank you very much, Matteo, for a very interesting overview on cellular materials under fatigue. And
thank you to you and to the audience. I wish all you a good continuation.
Thank you very much. And then I want to switch the focus a little bit to the industrial problems, and I want to welcome Armin Wiedenecker from First Alpine Additive Manufacturing and to the stage, Global Strategy and Business Development.
Yeah, hello. Thank you, Mr. Torgersen, for this nice introduction, and thank you and also Professor Stampfel for the invitation that I can make a talk here at this conference in the plenary round. As you mentioned, my name is Armin Wiedenecker. I'm the Managing Director of the First Alpine Additive Manufacturing Center located in Düsseldorf. And we are, as the name says, a purely powder bed oriented company. So our focus is to develop, based on the materials we produce internally, new products for the market. So I think the presentation fits pretty well together with the first plenary we heard before. But as Mr. Torgersen mentioned, we are going much more into the industrial application based on that what we learned before. So I will start with a very short overview about our group. So the First Alpine has roughly about 50,000 employees and about a turnover of 11 billion. We started our additive manufacturing journey in 2013 and have recently built up several centers around the world where we produce parts and offer services and doing a lot of development with the powder bed technology, but also with laser metal deposition technologies. Furthermore, we have internal powder production in 2 locations with the companies Böhler in Austria and Uddeholm in Sweden. So what we're really trying to cover is the full value chain from powder development, powder production, over parameter development, design and simulation, the production of the parts. And I think most of the presentation will be the interaction between the right powder and the right production of it, and strongly related to the design and simulation out of it, but also like the final machining and finishing of the parts we can do internally. And after this very short overview, I want to come directly to the part or to the main topic. And we are talking here about it's called Flow Filter V. It's a product. It's in the area of plastic injection molding, and it's a nozzle filter. So in fact, as you see here in the picture, from the left side, plastic is flowing through this part, and irregularities or unmolten particles or unwanted particles will be filtered out via this product. So this is a full replacement. So this is a substitution of conventional produced products, and it's perfectly suited for additive manufacturing. But what you can see here already in this picture is like you have a high complexity, you have some kind of lattice structure in there. And the big challenge, what we see here is this part generally exists on the market in 4 or 5 dimensions. But the customer need here would be 50 different dimensions. And here, additive manufacturing and the design and production capabilities of this technology gives us the opportunity to really make individual parts for customers, but for a price which is close to serial production. And this is only necessary via a very good design solution and very stable parameter development to really have a constant quality in producing these parts. So to show it a little bit more, this part, so these are on the right lower side, you see competitor parts, for example, from the company Hasco, which are conventionally produced. You see there's a lot of machining and drilling, etc. needed for that. And this is rather efficient if you do it in a high quantity. But if you can imagine how many operational hours are in machining and turning and drilling in these parts, there is a rule of thumb to have about 1 hour programming for 1 hour machining. So it might be rather efficient if you produce 10,000 exactly of these designs, but if you need 500 designs, the programming of that, it's super expensive. So the function of the part is, as mentioned before, aluminium is flowing through, and to eliminate any unwanted areas, to protect the plastic parts afterwards, which are produced, and protect the tools which are using these plastic parts. So here, additive manufacturing is coming in, and this is really only from the flow through. You have several advantages in here to have reduce the injection pressure, you reduce the maintenance and downtime cost, etc., without going that. So it's really suited for additive manufacturing. And you also see here we have done some pressure drop results. So as introduction that this is really worth to go for it. And you can see here in green our pressure drop, and on the left side you see if you don't use any filter at all. So based on the design possibilities additive gives us, we could really significantly improve it to the competitor products or existing products, and that we, depending on the size of the part, are close to almost having no filter and just a ring inside the injection molding machine. So that really has a customer advantage by doing this by additive, but it's still the problem. A lot of different designs means a lot of costs. So, and now the question is how to overcome that. So we discussed with several partners, and we had very good discussions with Siemens and what they are providing for solutions, and especially in the area of parametric design. So is it possible to take this part, create, I would say, ruling geometries and create a parametric design where we can reduce the design cost by 80%, so that we can really have individual designs for each customer. Maybe you can have a very simple Excel mask, or you do it on a website where every customer can really create a tailor-made design. So this would be the step one. And the second would be, how can we create a good production volume for that? So this ruling dimension needs to be defined, and for sure, a wide range of available dimensions must be available that the customer really gets the benefit. So here you see the flow through. We have some, for sure, some additive manufacturing restrictions. So we set an angle not more than 45 degrees in flow directions to have no sharp edges. So what you see here, this is not the final geometry, so that's a simplified geometries. So for sure, have everywhere radio and etc. And I think we have seen in the presentation before, it's very important to understand upskin, downskin, which surfaces you have where, how many sharp edges are allowed or not. And yeah, and also for sure we need some mechanical properties which must be fixed independent of where on the platform the parts are located, and also how big the parts are. So how must this structure look like if the part is very small and if the part is very large? That is resistant against the 2,500 bars. So it's some kind of a serious pressure which can get onto this part. So what we see, also a big challenge every time in additive, is to have a high productivity, high resolution, high quality. So you have really find the way to produce maybe some areas with a maximum speed, some areas with highest resolution, and everything with the given quality to be also cost effective. So what we really had to do is like to tailor-made the parameters to this product and to the various requirements we have for this. And what you see here in a schematic design is how we can mix various designs and different designs on one platform to optimize the production cost. I think it's well known that the fuller the platform, the cheaper it gets. But for sure, I think everybody knows this. You have some no-build zones on every platform and every machine, depending of the filling grade. So you really have to understand: can you really pack it with 90% density, 80% density, and which are the areas you cannot go deeply in? And here we get a little bit more in detail. So we are a lot of working with the in situ process monitorings. So with the online tomography and the multiple monitoring system from EOS, here where we also produce these parts, to really understand the interaction between the produced parts and the positioning on the platform. So the fuller the platform is and the parameters you use, and in fact this was done for each and the final parameters, we have to do that. Additionally, besides how can the platform be fulfilled and where we can guarantee really the quality what is needed, the parameters via statistical design of experience must be optimized in a way to reach the quality what is predefined by the customer and by the application. So that's definitely going into the analytics. We go via EBSD analysis to understand the properties, to optimize the heat treatment for it. And what we have achieved is that via really optimization of the parameters by maximizing the utilization of the platform with the material we used, that's Udeholm EM Corax, we could reduce the costs, in fact, by almost 50%. So this was really only by strong interaction and better understanding of the parameters. And so we reach still a very high surface quality where it's needed. We have very good values for the mechanical properties, but by almost half the cost. And this brought us to a level where we are definitely cheaper, only for if we produce one part, always the same part, than conventional produced. So via optimization, the parameters, and I think we have seen it before that just on the surface, what I'm discussing now and all the dev work, what was in behind, was not shown here. So how much work it is, but this shows the potential. If you really understand this, what was discussed in other presentation, then you can really get a very good business benefit out of it. So for sure, we also achieved the mechanical properties and all the areas what are relevant, and these are definitely conventional to the comparable to the conventional material. What I think is a necessity to provide a product like this and really sell it as a serial part product. And this must be given independent of design, independent of the dimensions, and also independent on the area of the platform where you have these parts. So, and here I said about these ruling surfaces and ruling designs. So here we are deeply into the area of parametric design. And as mentioned before, we strongly worked and cooperated here with our partner Siemens. So where you define which areas can be modified and which must be the first, which gives the ruling of the design modification. So you see here variables, colors, how you different design areas and dimensions put. So you have some editable data, like that's the length and the diameter and like the whole diameter, what is here rectangular. And sure, you also have some support, which is removed after the production, but it's also important to have a right support for this part. And so this is the base where you start, okay, which are the most important dimensions? And here it's really like a ruling. So what is the first most important, what's the second most important, and all the others have to adapt on it. To really create, I would say, a lattice structure, which is strong enough to resist the requirements, but also is, I would say, open enough that the maximum amount of plastic can flow through. So the more holes we have, the better it is, but for sure, the more holes we have, the more reduced will be the resistance and the strength of the part. And this must be perfectly aligned to each other. And here's the ruling of the geometry is super important. So you see here the parameter interface. So where we have defined five master parameters, which are the ruling ones, and it's called 83 slave parameters. And if you have defined everything like that, so the design procedure is really simplified a lot. So in fact, within few seconds or minutes, new designs are developed. And if this mask is really finalized, then it's really working that every customer can on demand, live on the website with few mouse clicks optimized via these 5 master parameters. They are tailor-made design for it. And this would be these 5 parameters. And then afterwards, every customer can get his individual design. And I just showed you some parts here, which were really done within a few minutes. So I have 7 designs with different diameters, different lengths of it, different mesh sizes, but all of them are kind of optimized for the maximum of holes, so to reduce the pressure drop, but also to still resist the mechanical properties or like the requirements we have from the application. And I think this is one of the big challenge. And to create one of these, it's normally, if you do it by hand, manual design, it's really hours and hours of work. And now via one-time effort, we could really reduce this to, in fact, few seconds and maybe some calculation of the computer, but this is like irrelevant for us. So here the possibility increased a lot to really satisfy exactly the customer needs. And before they had only the possibility to choose, okay, which of the standards are close enough and have to add additional rings or whatever, or modify their nozzle system in the injection molding machine. And now we can really tailor-made it to the individual specifications. And to have an overview, so on the left side, you see the manufacturing. And as I mentioned before, we are optimizing the parameters. We could really reduce the cost per part by fully utilization of the platform to a level where we are cheaper than a conventional production. So by optimizing the areas, and this would be, in this case, the outer ring with a high productivity, have a high resolution of parameters in the inside with a very good surface quality, with that we don't have sharp edges, and really an optimization for the requirements. And for sure, understand how fully packed we can utilize the platform, so we can really get the pure additive manufacturing costs below the level the conventional manufacturing costs are. And additional, as mentioned, we also worked on the topic of design costs, where we said, okay, one design or 2 designs are rather cheap to do. But if the customer asks frequently, or many customers ask frequently, I need 5 millimeter more diameter, and I need it 10 millimeter longer, then there's a kind of limitation of human resources we have internally, and no customer would pay 1 day extra designing cost for 3 filters. But with this one-time effort of this parametric design, we had an initial effort, which was definitely higher than if you design 2 or 3 designs. But based on that, we have kind of a stable cost. So it's like a really minimum adaptation sometimes needed, and are independent of the design quantity. So by the combination of an parametric design and an optimization of parameters, it was possible to create a product which is very customer-centric, which is superior than the conventional product, and helped us to have a very efficient also internal route. Yeah, so this was my last slide. Thank you that I got the possibility to have a presentation here. If there are any questions, please don't hesitate to ask.
Thank you very much for this industry perspective on parametric design and mechanical properties of EM parts. I'm sure there are some questions for your talk. I have a question regarding the holes. Are you just optimizing the number of holes, or are the shapes of the holes also important for your application?
So the holes in reality are round. Mm-hmm. It's depending a little bit on the size, and I would say the shape is for sure you have to reduce every stresses you have. Therefore, you have round holes here, and I would say we have 2 versions out of it. We have round and rectangulars, depending on the size of it, and there's always a difference, and we have seen it before. So the perfect file is not the part afterwards. So it's not always the same what you have in the CAD file and what you have afterwards printed. And so we had to do some modifications here. For sure, we have to try to reduce the stresses, so you don't want these edges, what you have a lot in this rectangular design. And then it's getting what is rather a challenge was, especially in the design, how to optimize is to get as many as possible with still some strengths in the part. So here, this was really, I would say, much more work than we initially thought, and also like Siemens thought in the beginning, that we gave a very good algorithm behind here to optimize this, I would say, relationship amount of holes to strength of the part and minimum wall thickness.
Okay, thank you much. I think Anton was the first to raise the hand.
Yes, thanks. I have a question. You showed a slide where you have a whole build plate of parts printed and you optimize the productivity, something like 50% of build time, if I understand it correctly. Can you tell us how you don't have to give details, but what is your approach to that? What do you use to improve the build time in this case?
So at first it was very important to understand how full we can really pack the platform. So how close each filter can be located to each other without having a negative impact on some filters. You know, there's a lot of scattering. You create a lot of dust and dirt in the process, and you see it in the left picture. So how fully can you pack the platform? And this in relation to how fast can you print. So if you go with very high energy density, you probably have, say it very simplified, a more dirty process, then you have less energy density. So we have, if you look at the filter.
And how many are not showing your screen?
Oh, okay.
Yes.
Work right now?
Yeah.
Okay.
Yes.
So So here, for example, in this multiple monitoring or OT pictures, you see, for example, the interaction in some areas with other areas. So this, I think, is very important to understand this, how fully packed can you really with the quality what you need. And if you look at this filter here, you see you have a rather, I would say, very simple geometry on the outside, the wall, but it needs some strength. So this can be produced with much higher build-up speed, I would say, than the internal ones. So if you try to look for parameters, maybe you can produce this with 90 or 60 microns, a layer thickness, and internal with 30 microns or something like that. And as this is only, I would say, kind of lattice, you always have the problem with the vector length. So if you have too many small areas, and depending on the machine and how the scan strategy is set up, you have to try to optimize also the sizes to create not too many jumps between the lasers, because this increases the speed a lot.
Okay, thank you.
And I think the next is Jürgen.
Yeah, so first, thanks for this very impressive talk. I have a question regarding cost. As you pointed out, this is always very important. In your view, is the costs, are they more, in this case, more dominated by the material cost, or more by the process cost, or maybe also by the cost of the personnel designing these things? So in your view, what's the main limiting cost factor there?
Yeah. So I think the reason why we chose this parametric design and why we get this was really that for all these non-standard parts, and there were so many requests from customers, it was definitely the design cost. If you say, okay, if you think about one designer, one working day for creating one part, an optimized design, it's easily 1,000 euros or something like that. A filter of this costs between 100 to 300 euros, depending on the size. And if a customer needs 2 of them, they are not willing to pay, obviously, 1,000 euros extra. So this was really a limitation for having, a lot of non-standardized parts. So definitely in this way. So for the simple production out of it, here I would say it's still the machine costs. And from a business perspective, these parts are rather small. So I don't know if, I think on the last slide I have here length of it. So you're talking about maximum 100 millimeters of length, but this is really the large ones. What we have here limitation is, and that's maybe not everybody considers, is if you work on an EOS M290 standard machine, these are nice build jobs. If you really fully pack it, maybe one day, that's a fine job. If you would change, for example, to a 4 laser machine, to an EOS 404, to a Renishaw Trumpf, whatever, then you might have the challenge that you have just a 6-hour build job. And from a production perspective, if you go there and say, okay, I only every 6 hours I can start a new build job, then you have to think about, do I really have 24/7 operators in my production facility? Or do I prefer to have the machine running 24 hours and I have just once a day have to change the platform? So this, I think, is something what not everybody considers on the first side, that with multi-laser and what's cheaper. And as it right now, the machine costs are definitely the bigger portion. So I would say of the EM produced parts, it's definitely 80%. But as the machine's getting, I would say, especially cheaper over the time, or must be cheaper, then for sure this will change to the powder costs. But we also have seen a serious drop in powder costs here. So we are talking here about the corrosion resistant tool steel grade. This costs, I would say, 3 to 4 years ago, 150 euros. Now you're more in the area of 60 euros. So that's a really good drop in material costs, what definitely helps to get to a level where you're just cheaper than conventional production.
Yeah, thanks.
Right, thank you very much. Are there any other questions? If not, then we are already at the end of our session now. So we are perfectly in time. Thank you, Armin, for this very nice insight into industry and also into the costs, something that we as researchers do not consider so much, at least on the operator costs. Yeah, so then I would like to close this session and welcome you all again in this session again at 10:40 for a session in AM Aerospace and Lightweight Design that is chaired by Professor Louis Rees and starts with the presentation of Lukas Husmer. So see you soon. I hope you enjoyed the session and enjoy the conference.
Hi, good morning, Luca. How are you?
Good morning, everyone. Good morning, Luis. I'm okay. Yourself?
Yeah, thank you. Well, let we wait just more 1 or 2 minutes.
Okay. I'm sharing my short presentation then.
Okay. Okay.
Yeah. You should be able to see it.
Yeah, it's okay now.
Okay.
Well, I think we are on time. So good morning to everyone. My name is Luis Reis, so I'm professor in Instituto Superior Técnico in Portugal. We'll share this session with my colleague, Professor Adil Jesus from University of Porto. And well, after the 2 very interesting presentations from this morning, we are going to proceed with session 4, additive manufacturing in aerospace and lightweight design. Well, welcome to all of you. I hope this session will be fruitful to everyone. We have 11 papers for this session, and I invite you to pose questions and comments in the chat or raise your hand. Don't forget that. Well, the first paper is for Professor Lucas Susno from the University of Sheffield. I think everyone knows him. So the title of his work is Nominal Stresses to Assess Damage in Notched Additive Manufactured Steel Subjected to Constant and Variable Amplitude Multi-Axial Fatigue Loading. So Professor Luca, the stage is yours. You have 2-3 minutes for your short presentation. Okay. Please go ahead.
Okay, thank you, Luis. Thank you for your kind introduction. So basically, the aim of this work is to check if our multi-axial fatigue criterion, that is the modified Wheeler curve method, can be used along with the nominal stresses to estimate the fatigue lifetime of notched additively manufactured metallic materials, when these notched components are subjected not only to constant but also to variable amplitude multi-axial fatigue loading. Okay, cutting the story short, the modified Wheeler curve method is a critical plane approach where the basically fatigue damage is estimated via the shear stress amplitude relative to the critical plane, which is defined as the plane experiencing the maximum shear stress amplitude. But it also depends on the amplitude of the stress perpendicular to the critical plane, as well as on the mean stress perpendicular to the critical plane itself. We can combine these stress quantities to obtain this stress ratio, and this stress ratio is sensitive to the degree of non-proportionality of the applied loading, as well as to the presence of superimposed static stresses. In this specific context, our stress analysis was done by referring to the nominal stresses referred to the net section. So all the calculations were done in terms of nominal stresses. Clearly, this approach is, quite complex in order to use and to apply. But anyway, no matter the complexity, what you really need is to basically calibrate your approach. And to do that, what we did was using the uniaxial and the torsional fatigue curves, and we corrected the 2 curves using the conventional fatigue strength reduction factors, which are basically the ratio between the plane endurance limit and the corresponding notch endurance limit. So you can do that both for the torsional curve, the red one here in the graph, and the blue curve. Okay. So this is the general idea. So we checked the accuracy of this approach by using a large number of specimens that were manufactured using the direct metal laser sintering technology. We use as a material AESI 316L. Here you can see some of the key manufacturing parameters, and we manufactured a number of bars, and starting from these manufactured bars, we put the notches using a conventional lathe, and in particular we put 3 different notches, having resulting in an axial KT ranging between 7.2 down to 1.4. These specimens were tested under the combined detection and torsion. We considered both in-phase situations and out-of-phase situations, but also we considered both fully reversed load histories and load histories characterized by a load ratio equal to 0. And these loading paths were applied not only considering constant amplitude load histories, but also by exploring variable amplitude situations. This is the load spectrum we used to apply these various loadings. So having generated the data, after that we had to calibrate our approach, and we used the fatigue strength regression factors expressed this way, where Q is the fatigue notch sensitivity and KTT is the stress concentration factor under torsion, and KT is the stress concentration factor under tension. So by using the uniaxial fatigue curve generated by testing the sharply notched specimens, we obtain a fatigue sensitivity index Q equal to 0.082. So we used this sensitivity index together to the corresponding value of the stress concentration factors to estimate the fatigue strength reduction factors under tension and torsion, which were the 2 factors we needed to calibrate the approach. And overall, this is the accuracy. You can see it for the blunt, intermediate, and sharp notches. This graph plots the experimental number of cycles to failure, NF, versus the estimated number of cycles to failure, NFE. And as you can see, okay, there is a little bit of scattering as expected, because in the end we were dealing with the 3D printed metal. So again, as always, the presence of the internal defects played a major role in defining the overall strength of the material. But in the end, we managed to obtain, for the constant amplitude case, predictions which were quite accurate, or at least falling within the scatter band of the notch uniaxial fatigue curve used to estimate the notch sensitivity index Q. In a similar way, this is the accuracy we obtain under variable amplitude fatigue loading. We had to use, and here we obtain this level of accuracy by simply taking the critical value of the damage sum equal to unity as recommended by Palmgren and Mine. Again, a certain level of scattering associated with the defects characterizing the material microstructure, especially let's say the subsurface manufacturing defects, but overall, again, a very good accuracy. So we can simply conclude by saying that the modified Wheeler curve method can be applied along with the nominal stresses also to estimate the fatigue lifetime of notched additively manufactured metals. Thank you very much.
Welcome. Thank you very much, Professor Luca. So are there any question or comment from the audience?
Yes.
Okay. Oh, hi, Abilio. Good to see you.
Luca. How are you?
I'm okay. Yourself?
Yes. Good morning, everyone. And well, I would like to say that it was a very pleasant work, this presented by Luca. And I have just one question, maybe a minor one, but just to clarify myself about the notches. Were them machined or as built? And in the case of as built notches, how do you deal with the roughness on the theoretical stress concentration factors?
That's a good question because, you know, those notches were manufactured from the 3D printed bars using a lathe. So in a way, we put ourselves in a better situation because, you know, the notches were more regular, the surfaces were manufactured, so less roughness. We did run as machined. And I would say that without not even any heat treatment, so really as machined. And honestly, the material was as strong as a piece of chocolate, really. So I really don't know how to answer your question because either you do a lot of post manufacturing work in order to get good material properties, or the material you get in the end is so weak that I don't really know if it's relevant from an engineering point of view. This is the reason why it's difficult for me to answer the question. I can tell you that if you do all that post-processing work, we know, like treating the surface, have the specimen and so on, the components, you can get good mechanical properties in terms of fatigue. If not, stuff, because it's you know, in terms of fatigue, the strength is very, very low. Just you know, we know, just to give you an idea, we know that for conventional steels, the ratio between the UTS and the endurance limit is around 0.5. For that material, was around 0.05 with no treatment at all. So, you know, the first specimens, we broke the first specimens straight away because really we were trying to find the first stress levels and they were too high. So this is the reason why it's difficult for me to answer your question. I suppose that so honestly, I don't really know because considering what we use, as I said, without any post machining treatment, you would get a very bad material in any case.
Okay,
Thank you. Thank you.
We should move on. So we have a question here in the chat from Maximilian. Why did you take this heat treatment?
Exactly for that reason, because we were trying to reduce the internal residual stresses. We were trying to create a material which is more homogeneous. And I think that, you know, going for a post manufacturing heat treatment is quite common with 3D printed metals because it's the best way to get a little bit a better fatigue performance.
Yeah. Well, any other question or comment from the audience? Well, if not, we should move on. So thank you again.
Thank you very much. Thank you, Luis, and thank you, Abilio, for the question. Thank you.
Okay. So the next presentation is for Professor Rhys Jones. Okay, he's with us. So, adjunct professor from the Faculty of Science, Engineering and Technology, Swinburne in Australia. And the time of his work is characterizing crack growth in scalmalloy. Well, Professor Jones, can you perform a short presentation of your work?
Can you see my presentation?
Yes, we can see it.
Okay.
Can you put in full screen?
That's what I'm trying to do.
Okay.
There we go. All right, so moving on.
Yeah. It's okay now.
Scammalloy. So the question you have to ask is why scammalloy? Well, as we've just heard in that talk, a lot of additive manufactured materials have quite poor mechanical properties. By mechanical, I mean yield stress, ultimate strength, and relegation to failure. Scammalloy is not like that. It looks to be the gold standard, and it's got properties which are comparable with that of 7000 series aluminum alloys. On this particular slide, what I've presented is the DAD and delta K curves for scammalloy from the literature at 0.1 and 0.7. If you look carefully, you can see, yeah, the results are similar to 7075 T7351. Okay, yes, I've even got on this particular slide, crack growth curve for laser powder bed fusion commercially pure titanium. Another day, another talk for another day. All right, now you've got to have a similitude parameter. And what you'll see in this particular slide is that for metals, if you plot, and this is 7050 T7451, which is the most widely used aluminum alloy in aerospace. And what you got here is a lot of short crack tests at R ratios from -0.3 all the way up to 0.7. And you've got comparison with long crack tests done by NASA, done by Australian Defence Department, etc., at a variety of R ratios. And you see the classical spread, and people say, oh, you have a short crack anomaly. Well, what you find is that if you express the curve, instead of writing as DADN, instead of delta kappa, with this delta kappa up here is the Schwalbe crack driving force of the Professor Schwalbe similitude parameter, then all of these curves collapse. So this becomes a valid similitude parameter. Okay, what happens if you do the same for additive manufactured material? Well, here is 53 tests on additively manufactured Ti-64 done by laboratories all around the world, including Delft. The Delft ones these at Coventry, by Airbus, a whole pile of them. And if you do the same thing, and you plot them in terms of delta kappa, what you see is that all of these curves, which are crisscrossing and nasty and messy, all collapse onto a single curve. So what you can see here then is that these 53 tests in additive manufactured materials are uniquely characterized by the parameters A, which is the cyclic fracture toughness, and the threshold term. Okay, moving on. So now let's go back, have another look at crack growth in, I don't know how to do this. I need to get this one out of the way, don't I? Never mind. Okay, let's now look at crack growth in additive manufactured scamalloy again. Same curves. Now the plots. And what you see is the scamalloy tests now all reduced down to a single curve. That curve is, to all intents and purposes, very similar to 7075 T7351 and slightly worse than 7050 T7451. All of these curves are collapsing over 4 orders of magnitude in DAD and delta K. So the difference in the additively manufactured curves, scamalloy, is like the difference in additively manufactured Ti-64. In other words, it's purely governed by 2 parameters, namely the fracture toughness, the cyclic fracture toughness, and the threshold. And the curve is, to all intents and purposes, the same as 7050 T7351. Wow. What this means, if you take it in summary, is that scamalloy is an attractive material for additive manufacture of aerospace parts, limited life parts, and you can think of either replacement parts or attritable aircraft, UAVs, satellites, etc. And it looks like crack growth in scamalloy can be represented by the same equation. And the resultant DADN versus delta kappa relationship is very similar to that. The commonly used 7075 T7351. The challenge now is to determine the curve needed for a durability assessment. But this curve must account for the large variability associated with the growth of small, short cracks. The upper bound, the DADN versus delta K curve for such a durability curve analysis should lie very close to the DADN delta kappa curve given in the talk. Why? Because for small cracks, delta K approaches delta kappa, and this falls out of ASTM E647 TTEF standard in Appendix 3. Thank you.
Okay, thank you, Professor Jones, for your presentation, So are there any questions or comments from the audience regarding this work? No? So I have, let's say, a question and a curiosity. You mentioned in your work, yes, can you hear me? Yeah.
Absolutely.
Good. You mentioned in your work that this alloy, scalum alloy, is, and compared with the aluminum alloy, is well, an exceptional strength stiffness weight ratio. Well, my curiosity is there any drawback from this alloy?
Look, never say never.
Yeah.
I think James Bond made a film on that. I'm not entirely sure. Never say never, but it looks to be at the moment the best thing for use to replace conventionally manufactured aluminum alloy parts. Now, I am aware, I mean, this material is invented by Frank Palm at Airbus, and one of his colleagues is giving a talk later in this series, and I'm aware that Airbus are looking into an even better alternative material. So maybe there's going to be any better material, but at the moment, it looks to be I'm aware that the US Navy think that this is the gold standard, but maybe there'll be a platinum standard soon.
Okay, I think Mr. Maximilian, can you put your question?
Yes, thanks very much for the talk, Rice.
Welcome to the session.
Yeah, I have one question. Do you have any issues with residual stress in this alloy?
Look, I don't know. I think the best person to talk to is the gentleman, the Airbus gentleman, is going to be on later on. The data that I've got is all associated with specimens that have been heat treated and annealed to largely remove residual stress.
All right, thank you.
Okay. Any other question from the audience or comment? Okay, my question. Well, it is a very interesting perspective from you. You try, let's say, harmonize the small cracks and long cracks and the overlap, also to take into account the different processes, right? So the ESIAM and the LPBF process. My question is how the model captured all these features, let's say, physically, how the model takes into account this. Can you detail a little bit?
Absolutely. There was a joint study between myself and Sarah in Milan and the Prague team, Jan and Andre, in which we found that we could uniquely relate the parameter to the change in the potential energy per cycle. And this turned out to be true, and the experimental work was done in Prague. This turned out to be true regardless of whether the specimen was built, was a conventionally built wrought material, or whether it was built using cold spray additive manufactured process. I should add that this particular material, if I remember correctly, and I'm not entirely sure I do, but I think it is, it was 316L. 316L, I think.
Okay.
Yes, the material was 316L, Rice.
Thank you.
Thank you. Okay. So if there's no more comments or questions, well, thank you again, Professor Jones.
Thank you.
And see you around. So we move to the next paper. Next paper is for Professor Sergio Amancio.
Hello, good morning.
Hi, good morning. Welcome to the session.
Thank
So
you.
Professor Sergio comes from the Graz University of Technology in Austria, and his work is influence of the composite structural parameters on the mechanical performance of additively manufactured composite metal hybrid materials. So please, can you do your short presentation of your work?
I just need to share my screen.
Yeah, please.
Have you allow me to share?
I think you are allowed. You cannot. Why the part? Maybe Professor Jones, can you stop sharing the? Professor Jones, can you stop? Yeah, you should stop. Share your screen. Okay, thank you.
All right.
So now, yeah, now I think it's possible.
Now probably I'm able to just let me see. Okay. Just 1 second.
Okay, no stress.
Yeah, I was just, I had to do an update. I think now it'll be fine. Just 1 second. Oh, yeah. So now you're probably seeing my screen, aren't you?
Yes, yes.
Okay.
Now it's good. Okay.
So good morning, everyone. Thank you, Dr. Hayes, for introducing me. Without losing time, I would like to acknowledge the first author of this paper, which is Dr. Falk. He's a past PhD student of mine. And so the topic, additive manufacturing of metal polymer hybrid structures, is a rather new knowledge area in additive manufacturing, which is basically composed of multiple step strategy. So basically, we are fabricating the metal, which could be through traditional ways, such as subtractive and formative ways. So cutting, drilling, forming, as you can see, milling in this picture, or through additive manufacturing as well. So using direct energy deposition or traditional powder bed-based fusion processes. The idea is to produce the metal and then hybridize the metal through 3D printing, polymer 3D printing process. So in the case of composite nowadays, for the continuous fiber reinforced 3D printed polymer or composite, we have the FFF method. So one important thing is to how the surface of the metal is before the hybridization step with the polymer or with the composite. So normally traditional technologies use it for adhesive bonding as a surface treatment, pre-treatment can be applied and should be applied, but also use, for instance, the potential of additive manufacturing of the metal to create micro lattices, pins on the surface, structures that will help on the micromechanical anchoring of the polymer and the composite on the surface of the metal. Ideally, you should work with process optimization methodologies such as design of experiments, but also in our group in Austria, we are increasingly using machine learning in order to optimize the process. Of course, CFD and FEM modeling and simulation also helps in order to optimize the process, the manufacturing process, in order to get the hybrid structures as we see in this example here. A small stringer skin panel printed with a skin of CFRP and a core in the skin made of honeycomb structures to decrease the weight. So the stringer is aluminum from the 2000 series here in this example. So our process that we applied for a patent is called adjoin. So this the additive layer manufacturing of sandwich type of structures. In this example here, we have an extrusion, an extruder, so FF printer composed of 2 extruding heads, one for the unreinforced filament and the other for the fiber reinforced filament. We have a building platform which is heatable where we fix the metal, which was produced in advance. And then we start depositing a first layer, which we call coating layer, which is the same polymer matrix of the composite in question, but without the reinforcement or with short fiber reinforced filament. So we go further until we deposit the layers of the composite and form then a structure, in this case, in this example, a simple single lap joint. You can do and turn the parts. You can use other type of configurations where you have, for instance, the preheating through other heat sources such as laser, or you can have smaller modifications of the extruder, work with double extruder head, but the principle is basically as shown here. Examples in the area of aircraft, but also extendable to other structures like in automotive can be seen here. So local reinforcements, as we show in the example, but also parts where you can combine internal honeycomb structures so that you can decrease the weight of your structure using the flexibility that you have with additive manufacturing. So the objectives of this work was to evaluate the influence of the composite layup. Yeah, so the composite parameters on the quasi-static lap shear force of aluminum 2024 reinforced with polyamide 6. And then compare that with reference adhesive bonded joint. So we use the aluminum 2024 with T3 temper, so 2mm roller sheets, which were pre-treated with sandblasting to increase the surface roughness at this case. And then we work with commercial available filament from arc forged, so PA6, and continuous fiber reinforced with PA6. Carbon fiber reinforced, as you can see here in this picture. You can have more details in the long presentations about the properties of those materials. In this work, we work with a Mark Forged tube printer with a modified heating system where you could fix the specimens and control the heating temperature during in a better way during the printing process. So we use a design of experiments of a 3K full factorial with 3 different factors. So of the composite parameters, let's say, so the number of layers, the distribution of these layers within the thickness of the printed composite. So we call alternate mid-plane bottom and mid-plane top, which is like this. The alternate, we have alternate layers of unreinforced and fiber reinforced composites. Here we concentrated all the carbon reinforced composite layers in the center of the part, so the mid-plane bottom. And then here we divided by 2 and put like on the bottom of the 3D printed part, and on the top 4 layers of carbon fiber reinforced filaments. We work with different orientations, basically 0, 95, and plus minus 45. So the results,
Sorry, Professor Sergio. I think we should move faster because
So we validated this model and selected optimized conditions based on this analysis of variance. Took the best condition, which was in that case the alternate 3D printed part.
Yeah.
And then compare that with adhesive bonding and got an increase in ultimate lap shear force in 35.3%, and in the displacement at break, so the ductility of 75% in comparison to the reference joints. So that's it.
We have to finish. Yeah. Yep. Well, okay. Thank you, Professor Sergio, for your presentation. So well, I have one short question for you, related with the industrial applications. Which are the main issues that this methodology posed to the application? Can you?
Yes, basically nowadays the limitations are related to the FFF process itself, which compared with other ways of producing composites, we have still a smaller mechanical performance. But there are other strategies, as in our work that will be presented this afternoon from Oberlehrer, which is a co-advisor PhD student of mine, and Professor Himmelmoser, which is also going to present in this session, where we apply, for instance, pressure and controlled temperature, so to help on the consolidation and the elimination of those intrinsic defects that we know very well from the FFF processes. So, and with the advent of the 5-axis and the robotic applications of the FFF, so I assume that that this process will be comparable to other traditional process like.
Okay. Yeah. Okay. Thank you very much. So we need to move on. Thank you, Professor Sergio. So the next paper is for Clarissa Becker. Please, can you stop share your screen, Professor Sergio?
Yes, I'm just trying to find where you are. Okay, no.
Okay, thank you. So, hi, good morning, Clarissa.
Hello.
Welcome.
Thank you for having me.
Yeah. Clarissa is a PhD student coming from the Technical University of Compiègne in France. And the title of her work is 3D printing continuous fiber reinforced polymers, considering material and physical variability towards robust design. Please go ahead, Clarissa.
Exactly. Thank you. I will try to make it short as we're a bit running out of time.
Oh, no problem. You have the time.
Okay. So I just wanted to quickly introduce you to a common approach for additive manufacturing of continuous fiber reinforced composites. And this is normally using topology optimization to create low volume structures. And those tend to be truss structures. And this is why we're particularly interested in investigating truss structures for the 3D printing. And then for the truss structures, it is of an advantage to place the fibers along the trusses to use the anisotropy of the fiber material. But as you might be familiar with optimization, it is very hard to obtain the exact optimal result. Normally, we get some kind of near optimum results. So we created 6 different near optimum results. We call them equally optimum structures because they only varied in their volume by less than 2%. And then we investigated their robustness towards uncertainties. So this is physical and material variability that has been introduced. And the methods we used for this was, on the one hand, the layout optimization tool to create those minimum volume structures. And then we used a certain generalized stresses method for the stochastic modeling. And a large advantage of this method, of the ESIAM, is that we can reduce the amount of finite element analysis that we need, and therefore come to a low computational cost. So instead of using a direct Monte Carlo simulation, where for each trial to evaluate the structure, we need 1 finite element analysis, which then could be easily 10,000 or 100,000. We only need 2, because we build a meta model and only study the meta model. So we conducted a study with those 6 designs. You see on the left the boundary conditions, and we applied 2 loads from the top. And our results show that even though the 6 designs were almost equally optimal towards the volume, they had a different robustness towards introduced variability. So we introduced a variability in the Young's modulus. This means this wasn't one constant value, but we had a normal distribution. And then obtained the mean value and also the distribution of the maximum displacement of the structures. And our conclusion is that structures which have more members tend to be more robust towards those uncertainties. And that's an interesting takeaway for future research, as we want to improve the numerical model to get closer to the actual 3D printed components. And this will be part of my further PhD research for the upcoming 2 years. Thank you.
Okay, thank you very much for your presentation, Clarissa. Are there any questions from the chat, from the audience? Any comment? No questions, no comment? I have one question for you, Clarissa. Well, the question is related with, let's say, the robust design. Which criterion should we consider, or did you consider in your model for considering a robust design?
The robustness here is measured as differences that we obtain in the displacement. And the lower those differences are, they're expressed by the coefficient of variance, the better the robustness of the design is, because the design is less sensitive to those variability. And in our case, we only introduced the variability in the Young's modulus, but of course in the future, because it's common knowledge that with 3D printing, we have uncertainties occurring. We have the uncertainties on the one hand in the material, so variability in the material strength, in the Young's modulus, and so on. But we also have geometrical uncertainties. So the dimensions we print are not exactly what they were supposed to be, how we designed them.
And also related with the loading.
Exactly, and then we have the loading, which also has a bit of variability. So taking all of this into account is very important if we want to create structures that come from simulation to direct manufacturing. If we want to skip the whole prototyping, we need to have models that we can trust and rely on. So therefore, we have done the first step, but the future research will be that we incorporate other uncertainties and their variabilities and study our structures and try to get them even more robust.
Okay. Well, we have a question from the chat from Jan Torgersen. As far as I know, the classic compliance model also favors more smaller members. Is the conclusion different here?
In this case, we have used not compliance optimization, but we've had the objective of reducing the volume. And yes, the conclusion here is the same, preferring shorter members. Often that was a problem, because if we have applications in structural engineering, it's not desirable to have a lot of small members because the manufacturing is very expensive. So with 3D printing, it's the first time that we can actually use this as an advantage. Okay. So yes, the conclusion is similar. And in the future, we will investigate on different formulations for the optimization, because there are multiple ones. This one, for example, just used the plastic criteria for the stress, but there are also elastic criteria. So we will get into the finding the best formulation for the optimization problem.
Well, okay. Thank you, Clarissa, and good luck for your PhD.
Thank you very much.
We move to the next paper. So the next paper is for Guilherme Guimarães. Is here, Guilherme Guimarães? Or any co-author from this paper? Compressive behavior of gyroid structures manufactured through ESIAM with carburizing steels. A numerical and experimental study. I'm not sure, but I think Guilherme is not here in the audience. Is correct? Let me see the online people attending the conference. Well, I think,
Luis, you can go ahead with the next one.
Okay, thank you, Filippo.
Yes.
So we move now to the next paper. And at this time, well, I give the word to my colleague, Abilio. Abilio, can you go ahead?
Yes, thank
you. Okay,
you.
please.
Good morning, everyone. Just to introduce myself, I am a professor at the University of Porto from Portugal, and I will assist Luis in this session, trying to help in the discussion. And I would like to ask the next speaker to move on to the short presentation of the work. So the next speaker will be Olivier Poncelet.
Hello.
Yeah.
Can you hear me?
Good morning. Yes.
Good morning.
So you can move on with your short presentation about roughness study by modeling laser powder bed fusion surfaces. Okay. Please.
Can you see my slide?
Yes.
Okay. So I presented here a work about modeling surface roughness of LPBF samples. And of course, it's different from mechanical failure in fatigue, but roughness is, as you know, is one of the main issues in a fatigue. So it worth to looking at it and try to control it and to understand it. So basically, the first idea of this work was to understand the contribution of the stratification to the roughness. So on LPBF samples, you know that you just stack mel pool together layer by layer. So it will create some kind of stratification here, depending on the layer thickness and the material. And we wanted through this work to know the contribution of these defects on the roughness, on the different kind of roughness parameters, such as RP, RV, RSQ, and RKU. But we also wanted to know when we have thin thread powder on the surface, what will be the impacts of thin thread powder. We know that it will, of course, increase the roughness, but we wanted to know how much and what is the contribution of the thin thread powder on the overall roughness of samples. And for that, we just built a geometrical model, really easy one. So it's not a rocket science here, but we did that just to get a comprehensive view on how the roughness behave on LPBF. And so quickly, the geometrical model was this one. We just stacked together some circle, where the radius of the circle is the size of the mel pool. The distance between the circle is the layer thickness of the process, which is about 30 microns or more. And we also add some errors on each of those parameters to be able to generate some profiles, as you can see here on the right. So depending on the level of the errors, we can study really basic profile, such as the first one here. And by increasing errors on those different parameters, we can study a much more complex profile, which are more realistic. And okay, so if you have any question about the presentation, go on.
Okay, thank you very much for your short presentation and contribution to this conference. Now I would like to hear the audience about any questions for this presentation. You can use both chat or microphone.
I have all the slide here, so if you have a specific question about one slide, I can show you the slide.
Okay, it seems that there are, for the moment, no questions, but I can make some comments and hopefully audience could later contribute also for discussion. But one of my questions is about the well, you talk in your presentation about the TED, the track energy density.
Yes.
So according to your suggestion, we should increase the energy density in the contour, laser contour. And then I think that, or I understand that in the infill process, we can reduce, we may reduce the energy. In your opinion, what could be the consequences of such kind of change in the energy density between the contour and the infill scanning of the material production process?
This is actually something we are studying right now, because of course when we do so, as we can see on this small picture here, we will have different microstructure between the contour and the core of the materials. And unfortunately, if we want really to get a really smooth surface here, we have to increase a lot the energy of the contour, but it will bring some defects such as keeling, which will bring really huge porosity on the contour. So it will have an effect, and actually I can't answer right now the question because we are still studying that. We did a lot of tensile test and fatigue test on such kind of a sample here to investigate this different microstructure due to the different TD we use between the contour and the core. So okay. I will be able to answer you in like 6 months maybe, but right now it's quite hard to tell you or to get you a right answer about that.
Okay, this is good, and your model is very interesting, and because many people are looking for roughness, effects on fatigue, for example, and I think we lack for a predictive model for roughness, taking into account the process parameters. So this is a good approach for the topic. So are there any questions from the audience?
Yeah, that was basically the idea of the model. It's to be able to understand such kind of curves. So when you change the TED here, for example, but it can be another kind of parameters, to be able to understand the curves you get from those kind of experiments. So when you want to proceed to a roughness optimization, of course, you will play with many parameters, but then you have really complex curve. If you look at RVRP, RKU, RSQ, it can be really hard to understand what you get. And that was the idea of this really easy model, to get just a simple but comprehensive study, idea of what's happening here.
Yes. I would have one question.
Yes, please.
Yeah, please could you comment on the influence of the material on the roughness you get?
Yeah, what I think is that the big difference between material will be the thermal properties of each materials, and this is why we really have different behaviors here. Even though we use the same TED for example here aluminum, silicon, stainless steel, and nickel, but they behave differently. They have the different thermal properties, which will bring different kind of defects. For example, in aluminum silicon, we have just few powder particles inserted on the surface until you reach really high TED. But for the other materials, such as stainless steel, you will get even for low TED, you will have a lot of powders inserted on the surface, and those defects will be linked to the thermal conductivity and thermal diffusivity of the material. So it's really difficult to optimize one material, roughness with one material, and apply that to another material, because it is material dependent. So you will have to optimize the roughness for each material differently, and the defect will be different. It will each time for each material it will be the same defect. Like you will have a lot of sintered powder, but it will depend on the energy you use, and
But still, this is unsolved. That we can predict the roughness just by bringing in the material parameters. This is not so easy. When I understand you correctly.
Yeah, it's really complex.
Okay, Thank you. Thank you very much.
Maybe a last question, if are any. No, so I make a final comment to this presentation. So can you comment about the unmelted particles? Because as far as I understood, you are generating unmelted particles in a random way, but I'm not sure if I understood precisely your idea. So do you have any predictive way for the unmelted particles distribution, or they are related to the process parameters? Can you comment on that or clarify
Yeah, for this model, we didn't have any prediction for that. And actually, I think it will be really difficult to know where will be the unmelted particle or synthroid powder. So here in the model, we just add particle on the surface with a constant spacing, because we just wanted to know, okay, if we have some particle on the surface, what will be the impact on the roughness? If the particle is on the top here of the valley or on the bottom of the valley, what will be the impact? But to predict that, of course, you will need some really complex simulation. It was not the aim of this work. And as far as I know, I really don't know if there is some kind of simulation or prediction about that. It's really complex because it's stochastic. So yeah, so I don't know the state of the art of the simulation about that right now. So
this was a provoking question.
It's a good question. I asked this question myself as well, but
yeah, that's why I asked you, because I am not working in this field, but since you are working, you could clarify what is the state of the art. So thank you for your help in this point. Well, I think we can go on. Thank you, Olivier, for your interesting presentation.
Thank you too.
So now we will move on to the next presentation that will be given by Franz Ria Mels-Moser. Sorry for my bad pronunciation of your name. So I believe you are a colleague from Sergio Amancio. So your presentation this presentation will be about 3D printing of continuous carbon fiber reinforced polymers. So Franz, you can go ahead with a short presentation of your work, please.
Yeah. So thank you very much for the introduction. I'm still looking where I can make the presentation visible for you. How is this possible?
You have a share button.
Yes.
On the bottom of the screen, the green button. Center.
I had it before, but I don't find it now.
Please, I don't know if you are with the full screen.
I have it actually. I have in the moment I have troubles. Doesn't work.
It seems that you should be able, because I have also this option available. So I think the speaker has closed his presentation. So if you maximize your window, you should be on bottom, but I cannot see your screen, so it's hard to me to. If you cannot share the screen anyway, you can comment about your. Well, you can give a few words without slides.
Yeah. This is possible actually. Now I cannot share my screen at the moment. So sorry for that. But I could explain what we are working on. So this is a research we make at the Carinthia University of Applied Sciences. As you already said, we have some collaborations together with TU Graz, with Professor Manzio. but we're different universities. And so our own work is on optimization of the whole process. And the first thing what we are looking, or what we were looking at, is why do we want to 3D print fiber composites? And one particular thing is that we look into nature, for instance, on the mammoth tree, then we can ask why it is possible for the nature to make such big structures which do not collapse by themselves. And the answer is quite easily to understand when we look at the microstructure of the redwood, of the wood of the mammoth tree. Then we see that this is some kind of a cellular structure which we see here, and this is the reason for how nature is making such lightweight structures. This can also be explained a little bit better if we look deeper into the theory maybe provided by Ashby, which is quite well known, these Ashby maps. And in these Ashby maps, we see all the materials in the world, and the best material in such Ashby maps would be on the left upper corner, means, for instance, very small density but very high stiffness. Of course, there's no real material in that region, and we can ask ourselves how close can we come to this optimum material. And then I have compared in my presentation 2 different approaches: fiber composite lattices and polymer lattice structures. And we find in this comparison that polymer lattice structures for the same rate are 100 times heavier, or have 100 times more mass than this same lattice structure made of composite materials. And this is the big goal. What we want to achieve is that we use this potential, which is 2 orders of magnitude. And if we not only look at the stiffness of a material, but also on the strength of the material, and in particular on the toughness of the material, then we find that we not only need fiber composite materials, but we need continuous fiber composites. That means fibers with very large lengths. And the question is then, can this be 3D printed? And as Professor Manzio already showed, there are some preliminary technologies, for instance, of Markforged or Anisoprint, where we can make simple structures and simple specimen, where all the fibers are just in the plane. But if you are considering more complex parts, for instance, we are looking at prostheses or other medical devices, then we find that the geometry is very complex, that the loading paths are very complex, and that therefore the fibers must be oriented in space, not in plane only. And therefore we need some technology where we can deposit the fibers in space. And this is done by what we call a multi-axis printing. We were quite successful already with 4-axis printing. It's a talk given by Alexander Berndt also today. And we are now working on 5-axis printing together with a company, HG3D, which is also in Austria. And we are developing in the moment a pilot line and the technology behind it, that we can produce products with complex geometries and complex parts. And therefore, we have to look at 6 different topics where we are working at. This is the material development. For instance, Professor Manzio said he's working with filaments of Markforged. But if you're looking at these filaments, you find a lot of voids, for instance, in the material. You find a very low fiber volume content, and in order to get better, the best material, we need to develop our own materials for that. Also for the design method, which is what Clarissa already has talked about, Clarissa Becker, where she showed that we need to take into account the variability of the material parameters during 3D printing. And in particular, we have designed one method which I call the dragonfly structure, which is based by on considering how insect wings are looking like, and we find that these insect wings also are made of lattice structures, which are strengthened by a membrane. And in particular interesting on this dragonfly wings is that these dragonflies, they have 3 different kind of knots in the lattice structure. One could be called a fixed knot, just for load transfer. The other one with a rotational rod, and the third one where larger parts of the wing can be bent, therefore making very stiff structures on the one hand, but also very flexible on the other hand, in order of how we combine these different knots. And this is where we're working on. Also on the hardware development, which is the print head, which also needs to be optimized for the material we use, and which is quite important, and a very, very large topic is the print path optimization. As I already said, that the fibers must be oriented in space, which is the correct layer is in the principal stress direction. But how is this to be done with the pilot line you have in house, for instance? So we started with the with this 5-axis printing, and the question was how has this 5-axis printer to be programmed that the fibers can be oriented in space, and this is also a PhD which we are working at. Yeah, this is short, and I'm quite sorry that you cannot see my slides, but
it was a pity. Okay, anyway, the presentation is available and very interesting and very inspiring also. So thank you for your introduction to your activity of your group as well. So now we have time for a few questions. I prefer questions from the audience. If you have any, please.
I have one question.
Yeah, Luis, please.
Yeah, but let's hear the audience. No questions from the audience?
There are no questions on chat, so...
Okay, my question is, well, it's a little bit later, but in this, let's say, if you are taking in mind any kind of issues related with recycling in the early stage of design, recycling materials.
Yeah, so there are 2 different topics, I think, when you address recycling. The one thing is recycling of material. For that respect, we are working with thermoplastic fiber composites, which has more potential for recycling. I think it's still not solved. And we have one project discussing together with Professor Manzio from TU Graz, where we want to take the fibers and to recycle them to make new filaments out of them. So this is still one sensible approach, of course. And the other approach is if we, for instance, combine materials, for instance, metal materials and fiber composites materials, we have to think of how to separate the 2 different materials again. And this is where your question comes in. I think we need to think during design of how we make the boundaries between the 2 materials, that we can bring them apart again after use of the components.
Okay, thank you.
Okay, Any more questions from the audience? It seems that there are no more questions, but I would like to make one, to ask one comment, at least. I understood that the technology regarding the long fibers printing is not mature yet.
Yes.
That we are progressing, but this is a promising field, but there are no commercial solutions for production of 3D complex parts. Do you believe that we will achieve that flexibility in one equipment for producing parts with changing easily the complexity of the part? So you believe that the robot with 5 axes would be the solution for getting such kind of goal?
Yeah, actually, if you look at the technology which can be used, I think there are two different possibilities. The one is the gentry robots with the, for instance, 5 axis, and the other ones is just industrial robots with the arm. And the question is, which is more successful at the end? And my feeling is that for smaller parts, the gentry robots will be the one, and for bigger parts, the industrial robots will succeed. But we will see whether I'm right or not, of course.
Yeah, that is. Regarding the fiber volume, I believe that is possible to have gradients in the fiber contents across the parts, right?
Yeah, sure. So if for instance, if you have filaments with larger fiber content and filaments with smaller fiber content, then you can make easily gradients. Or another approach would be to make the extrusion directly at the 3D printer. Then you can directly change the volume content during 3D printing.
Okay. Well, I think we are done. Thank you very much for your presentation and comments, Franz. Now I think we should move on to the next speaker. So I would like to call David Schimbeck.
Hello.
Hello. Good morning.
Hi.
So it is another presentation about Scalm alloys. Please go ahead with your short, with a short presentation, please.
All right. So can you see my screen?
Yes.
Perfect. So thank you for your introduction. I would like to give you a short overview of my research topic on the fatigue properties and the fracture peculiarities of our additively manufactured aluminum magnesium scandium alloy, commercially known as Scalm alloy. First of all, I would like to acknowledge all my colleagues working on this topic with me from Austria, from the Montana University in Leoben and the University in Innsbruck. So what is Scalm alloy actually? The material itself is very unique, as we have heard already in a previous talk. It's an aluminum magnesium alloy actually with minor additions of scandium and zirconium. And these minor additions lead to a quite very unique microstructure, a bimodal microstructure with a fine grained area, grain size approximately 500 to 800 nanometers, and a coarse grained columnar grained area. And the second thing is that we get a hardenable alloy, although it's just an aluminum magnesium alloy. So the thing is, we would like to go into certification with this alloy for aerospatial structural applications. As we have heard, the mechanical properties, the tensile properties are quite very high. So the problem is for the certification, actually, the problems are the fatigue properties. For additively manufactured materials, we all know that fatigue is a more or less an issue. As you can see here, it's just a small range of our experimental data, but we obtained endurance limits with our material from 80 megapascal with a very bad quality, build quality, up to even 360 megapascal endurance limit. So quite very high quality. So, but the reason or the problem for certification is that we need to take into account all the scattering. And here comes the fracture mechanics into the game, actually. So we would like to have a relationship between all, we would like to have a relationship that we can explain the scatter. And this is in the fracture mechanic tool, actually the Kitagawa diagram, which was elaborated on the first base here. So we try to get a relationship between the equivalent defect diameter in this case and the stress during the fatigue loading, and we see quite a nice relationship between those properties, making it easier to handle the big scattering. A second requirement now, which is arising during the last few years actually, is the cryogenic properties as we move on to our sustainable aviation goals, and we would like to have hydrogen as aircraft fuel. So we need to take into account the cryogenic properties for our static, for our structural loaded applications. So, and here Skalmalloy is quite very unique as well. Here you can see, for example, the tensile strength or the tensile testing curves for our standard heat treatment of 325 degrees Celsius 4 hours. And you see the blue curve, the room temperature testing with elongation of approximately up to 15% for good build quality. But when you test this material with the sun heat treatment at liquid nitrogen, you see a very dramatic embrittlement of the alloy, which is actually not common for aluminum alloys. We have to say we do not know the cause here at this point. Even it's very difficult to investigate those properties, but we have some kind of solution. If we go to the underaged state or even to the as-built condition without heat treatment, we see already a quite big improvement in ductility, making it feasible to go into a static loaded application at cryogenic temperatures for our future aircraft systems. So at this point, I would like to thank you for your attention and looking forward to your questions.
Okay, thank you, David. So we have now time for questions. Please don't be shy. You can use chat or raise the hand and make your comments or questions. If I may start with a question. Regarding this ESIAM field you are showing here, it is very, well, I think people are not surprised, people in this conference, about this scatter. But can you tell us about you have here different series of specimens. Have you tried to get a process window where you feel that you have some control? I saw your presentation, you said that it's very hard to process your alloy, but this is the best you can do for your alloy, actually?
No. So this is just to give you an overview to have different kind of platforms. We tried this alloy, different kind of suppliers even, and our in-house machines. But the point is, this alloy, as I've already mentioned in the presentation, this alloy is quite very difficult to handle, and we are quite very, it's a quite very unstable process, unfortunately.
Okay, because my question as a second part, because you have here the HIP process applied as well, and I was expecting some positive influence, and actually the scatter was more or less maintained even using the HIP.
So the HIP process is quite very difficult at this point because we have a very stable oxide layer within this lacquer fusion. So it's very difficult at this quite very low temperatures of 325 degrees Celsius to break those oxide layers and to have some kind of hip mechanism. Otherwise, if we go to higher temperature, we would have a quite, we would have an over-aged microstructure, which is not as good in the mechanical properties.
Okay, so we have here one question from Camille van der Rest. That is asking about the underage samples. Are those samples interesting from a fatigue point of view?
We have taken a look at these underage samples, and they are also quite very interesting from a fatigue point of view. Even if you go with some kind of modification of the process, you can have actually the same fatigue level, but with these underage state.
Okay, thank you. There are more questions?
Yes, please. Can you hear me?
Yeah. Yes, please.
Okay. The only thing I can comment about is if you look at the statistical variation of the fatigue thresholds between heat-treated and hipped, and you compare that variation with the statistical variation you get with conventionally manufactured materials. I'm really talking about titanium, where there's been Ti-64, where there's been a lot of data. What you find is that there's no statistical difference. There's no statistical difference in the fatigue threshold between a material that's been hipped, a material that hasn't been hipped, that's been hip-treated, and a material that's conventionally wrought. Now, that's not true with respect to the cyclic fracture toughness. But for the fatigue threshold, which is one of the things that David would be interested in, that kind of helps with respect to the difficulty in hipping.
Okay.
At this stage, I will shut up.
Yeah. I think it's, well, thank you for your comment. So I don't know if David wants to add anything.
Well, the hip or the problem, the issue with hipping is under investigation currently, because hipping is quite a very expensive process, and if you can skip it, it will increase your business case, and therefore we are trying to avoid this by even improving the build quality. And as we have already seen with non-hipped specimens, we can reach endurance limit of 360 megapascal with this alloy. So it's quite very high for aluminum alloys, and we are on a good way, I think, to avoid hipping.
Okay, I think we have a last question. So it's in the chat from Ian Torgerson. It's about H2 embrittlement. So is this alloy stable regarding hydrogen embrittlement?
We haven't seen so far any problems with hydrogen embrittlement, but we didn't take a closer look, as this investigation on hydrogen are just upcoming, and we really need to take a closer look. But until now, we do not have any. We do not think that it's a problem so far.
Okay, so. Thank you, David, for your question, your answer, sorry, and for your contribution to this conference. So I think we should move on to the next speaker. So I would like to call Mr. Ramesh Babu, that will present a work about wire arc additive manufacturing. Please go ahead.
Yeah.
With a short presentation.
Yes.
Yeah, we see
your. Yeah, you see you. Yeah, okay. And you can hear me. Yeah, yeah, good. Okay. Yes. Thank you for the opportunity, and thank you for the chairperson for allowing me to speak. I, on behalf of DNV and Linnea's University, I'm presenting this paper. And thanks to my colleagues who have are a co-author for this. So just to give a snap on this maritime components is that in the class, it's in the whole life cycle of the ships or offshore structures. On the ships, it has to live for approximately 25 years. So any component goes into the vessel, which is main, has to have at least a good quality for delivering. And the main background of this study was on a propeller, and the propeller is considered as a main propulsion system where it gives an efficiency. It's directly related to the efficiency, and also this material selection of propeller has to be withstand seawater corrosion, galvanic cavitations, erosions, as well as the waves roads. So normally the material is considered as nickel aluminum bronze, and traditionally this is done by castings. And in castings we have many segregations, sulfides, and also we have some porosities on things also. Using these castings, it's sometimes it's rejectable, and it takes minimum at least 6 months for making a new casting. So the new optimization for this VAM propeller was a motivation for us, and we want to check the real full-scale testing. There is many research was done in a scientific paper for tested samples, but we want to look at the results of the value at the critical areas. So we made a full-scale propeller, and we want to look at the high critical area, which is on a grade A and C. As per the FEA, we have that, and we use the normal process of VAM, and the thickness we printed was 70 to 88 millimeter on top, and we had this process parameter, and we had this both vertical and horizontal specimens, and we find that due to the heating process, we find some dendrites as well as some marginal martenstite layer, and we want to know whether this will be a effect for the during operation time. So when we done this, the testing results, both vertical and horizontal, we find the results are more or less good than the normal casting level. The main this testing was on the choppy, because the toughness was to be tested at 0, and yearly literatures they are tested at ambient temperature, but we are interested to check at the 0 degree where the ships will be moving on the ships. So it was coming up in a good 29 joules, which was quite an acceptable range, and as well as the chemistry was also within the acceptable range for use in the seawater conditions. And the total weight was around 520, and the total print was around 200 meters. Yeah. So on this conclusion that the propeller can be made, and it satisfies the ice stress areas, the mechanical properties were within the acceptable region. But still, we need to do some more benchmarking on fatigue and as well as the corrosion, which we are going to do it in next phase. Yeah.
Okay.
Thank you.
Thank you, Ramesh, for your short presentation now and for your contribution to the conference. Now we have time for questions. So as you see, we have very different presentations in this session, different material processes, and this is going to a larger scale now. So it is also interesting to understand the possibilities that additive manufacturing is opening or offering to us. So are there any questions from the audience about this topic?
Okay. I have a, okay, go ahead, Luca, please.
Yeah, yes, it's okay. It's a very short question, actually. Yeah, because it's interesting to see, because I also work with one, and also in a propeller here in the Netherlands. But I'm wondering about your the optimization of your processing conditions, because this is of course, like with the ship propeller, you have like a thicker region, and then when you get towards the edges, you have like a more thinner region. So how did you optimize how did you do the optimization of the process? Did you do like online control or offline control?
No, it was earlier. The control was done prioritized with the tool path. This was earlier designed with the initial tool path. It was designed, and then we went for the trial run, and then it was completed. So it was already existed with the AutoCAD CAD model.
Okay, so it was like during the design process.
Yes, design process it was taken. As you see, it was 70 millimeter at the base, and the tip is 8 millimeter. So we have a skewed angle in that. So that's the main reason of this motivation, that we want to check how the change of the arc when it goes into different thicknesses, how it will be contributing, especially on the stresses line. Yeah.
Yeah. Okay. And I assume that like for the 70 millimeters, you're probably doing some type of oscillation strategy, and then as you get closer to the tip, you have like more of a straight tip.
Yes, exactly.
Yeah. Okay.
Yeah. Yeah.
All right. All right. Perfect. Thank you.
Yeah. Come.
Please.
Yes, from my side, it's just a curiosity. As you're talking about a large component, as is the case, did you experience any warping influence or?
Yes, that's a good question. Yeah, initial phase, because we are not printing, we are a class society. So when we are witnessing the warping was a major issue when they have a thin sections.
Yeah.
So, but that they had to have a different, the optimization of the well bead was a big thing. So they have optimized the well bead and as well as the heat input when they give. So they have controlled the heat input so that there is no warping. Yes, that's true. The warping was a challenge. They have spent a lot of time to rectify that one. Yes. Yeah.
Okay. Thank you.
Yeah.
That's a question very interesting, because my question or my comment was in that direction as well, because it is possible to correct that distortion using post-processing machining.
Yes. Yeah. In this model, the allowance was given higher. So when it was machining, even if, as you say, the surface roughness is very high, the surface was around 200 microns when we build up, but eventually we need for a polished surface is around 1.6 RA. So there was a lot of machining involved in this, and as well as the allowance was given here again more, so that if there is any faces that can be removed, that one. Yeah.
Okay, I think we should move on. Thank you, Ramesh, for your very interesting presentation and contribution.
Yeah. Thank you very much. Thank you all.
So next speaker will be Jørgen Svenby. Are you there?
I'm here, yeah.
Yeah, okay. Welcome to this session. So I would like to ask you to make a short presentation of your work about additive manufacturing of Inconel 625. So please explain to the audience the important features or details of your activity. Thank you very much.
Yeah, thank you for the introduction. So I'm working for Prototech, and we are very interested in developing high temperature PEM fuel cell stacks. And that means also to make the bipolar plates. And since we are making very few units of a typical of one design, and also since the bipolar plates have a very intricate geometry, like internal flow channels and so on, therefore we want to use additive manufacturing to hopefully speed up the process and also reduce the costs. But unfortunately, in a high temperature PEM fuel cell, you have a lot of corrosion due to the presence of concentrated phosphoric acid and typical operation temperatures between 120 to 200 degrees C. So therefore, we need to corrosion test these samples. So therefore, we just printed tiny samples of Inconel 625, which is supposed to be a very good, relatively good resistance towards this type of corrosion. And in addition, we purchased commercial Inconel 625 to compare. Then these samples were machined to arithmetic roughness average of 0.3 micrometer to make sure that the surface is roughly the same before the corrosion test. The corrosion test happened so-called ex situ in a cell filled with concentrated phosphoric acid heated up to 150 degrees C using 3 electrodes, where one of the electrodes is the sample. There we can subject it to a potential and then measure the current, which is directly correlated to the corrosion. In addition, we measured the so-called interfacial contact resistance, which is the resistance of electrical conductivity between the sample surface and a GDL, which is very important in a fuel cell to keep this as low as possible. And typically during corrosion, the interfacial contact resistance tends to increase due to the formation of oxide layers and that kind of stuff on the surface. So to the results, so here you can see this is done at keeping the potential at 0.65 versus the reference electrode, which was a reversible hydrogen reference electrode. And then we measured the current over time, 24 hours. As you can see, the current density of the additive manufactured sample is higher than the commercial. In other words, the corrosion rate is higher for the additive manufactured. For the ICR measurements, then you can see that for the additive manufacturer, it's much lower compared to the commercial. And that can give an explanation why the corrosion rate of the additive manufactured sample is higher. In addition, we, from a plot that I'm not going to show here, but you can see on the YouTube presentation, you could extract these numbers where you have the corrosion density for the commercial 160 microamps per square centimeter, for additive manufactured almost twice the value, and directly correlated to this is the CPR, which is millimeter per year of corrosion, which is yeah, you can see the numbers is almost twice as well for the additive manufactured. We also did some scanning electron microscopy of the samples before the corrosion test. And as you can see, the surfaces are relatively smooth. Then after, then you can see that you have many black dots, which are so-called corrosion pits, which is clear damage to the surface. And as you can see from the commercial on the left-hand side and the additive manufactured on the right-hand side, it's clear that there's a bit more damage to the additive manufactured sample than the commercial. So to conclude, the additive manufactured Inconel 625 samples had a higher corrosion rate than the commercial Inconel 625, despite of having the same arithmetic roughness average value. The interfacial contact resistance of the commercial Inconel is higher than the additive manufactured one. And from the same images, you can see a larger degree of pitting corrosion on the additive manufactured samples. And yeah, what we I think will be continuous work is to try to optimize the production parameters, and also to maybe look into the material microstructure to really understand what's going on. So thank you for your attention.
Okay, thank you very much for your presentation. Now we have time for some questions. Are any questions from the audience? So this is a difficult topic, maybe, because it's for mechanical engineers, maybe it's not well, we have one question, one raised hand from Jan Torgensen, please.
Thank you very much for the talk. I know it's out of the mechanical engineering field a bit, but I can relate to this because I have also a project on fuel cells. I'm very interested in how did you come up with making the bipolar plate with additive manufacturing? Is it just the batch size that you are interested in, or do you see also other possibilities in design for the bipolar plate?
The goal is to produce the whole bipolar plate with everything included, like all the flow channels. And we have actually already 3D printed some bipolar plate samples, but corrosion is a major issue. So therefore, we wanted to test this ex situ, where we feel we have a bit more control of the corrosion processes. But we are also interested in 3D printing other parts of the stack.
Do you foresee that you can change the contact resistant issue between the bipolar plate and the gas diffusion layer with that approach? Because that seems to be a major obstacle for your high temperature PEM fuel cell.
This is a difficult question. I'm not sure. I'm not sure about that. We just need to try more.
Or in other words, do you think you can make some geometries that increase the contact area between the gas diffusion layer and the bipolar plate? Because I think that is restricting the current flow, right?
Yes, so you want to narrow the flow channels as much as possible, but at the same time you have to be careful to not making them too narrow. So there's this optimization there. So and every stack needs to be a bit tailor-made to really optimize the properties. One advantage with high temperature PEM is that you don't have vapor present, which you have in normal PEM fuel cells. So that makes it a bit easier to make the flow channels.
All right, thank you very much.
Thank you. Maybe I have one comment or question, Jorgen, about your talk about the future work that will be optimization of the processing parameters for additive manufacturing. Have you any clue about the physical mechanisms behind these higher corrosion rates for the additive? Or you are thinking of a kind of blind optimization process? Can you comment on this?
I guess it will be a bit of trial and error involved, but of course, if you can investigate the microstructure a bit more and know what we have and how the different parameters affect the microstructure, then it will be easier to tune the parameters so that we will get a more optimum result.
Do you have any idea of the porosity levels of your additive parts?
No, not at the moment, but we have, as I said, we have machined the surface also. Yeah. The surface gets really smooth and there's no porosity on the surface.
Yeah, but I was guessing that maybe you have very close to surface some pores, or they are hidden by the plasticity of the machining process, maybe. But okay, this is just some comments, and this, I guess, this is starting research, so you have a long way for sure.
That's true. We are in the beginning phase of this.
Okay, thank you very much for your presentation and contribution. Now I think we are, we need to move to the last presentation that will go to the fatigue direction. So this presentation will be given by Francesco Sausto.
Yes, can you hear me?
Yes, please. Can you a short presentation?
Yes.
Work, please.
Yes, can you see my screen?
Yes, perfectly.
Okay, So, good morning to everybody. Today I will show you our research activity about the fatigue strength mechanism under torsional loads of aluminum alloy, in particular an LC10 alloy obtained by laser-powered bed fusion. As a summary of this activity, the main aim is to investigate the axial and torsional fatigue of this alloy. To this aim, we printed several specimens with different geometries respect to the tests that we ran. The open questions that we want to figure out are the role of the internal defect and the rough surface of torsional fatigue, the effect of residual stresses that can be both introduced by machining operations and thermal history, and to propose a model that take into account these two effects. So from the point of view of fatigue tests, we performed axial tests at stress ratio of -1. From the point of view of fatigue limit, we got 200 megapascal for those machined specimens and 100 megapascal for those as built. So we got a 50% reduction in terms of fatigue limit. In terms of defects, we found 4 main families of defects. Machined specimens mainly failed due to sputters and pores very near to the external specimen surface, while as-built specimens failed due to superficial features due to the rough surface of the specimen and due to sputter particles attached to the external surface. So as you can see in the CIM analysis on the right, the dimension of the defects cannot justify the strong reduction in terms of fatigue limit. Due to this, we measured the residual stresses of both these two samples. So we got the compressive residual stresses for machined specimen and tensile residual stresses for as-built specimen. So looking at this graph, we can see that the main region due to the reduction between machined and as-built specimen in terms of fatigue strength is due to the presence of tensile residual stresses. So of course, the residual stresses alter the effective stress ratio at which the material is loaded. To take into account this effect with respect also to the defect size, we adopted a Kitagawa diagram that was built considering the Nasgro equation for the calculation of log crack threshold and Hayek diagram for the calculation of smooth fatigue limits. These two ingredients are of course a function of effective stress ratio. And as you can see, the effective curves in solid lines for both these two series fit very well with the experimental results that we got. For the torsional machined specimens, we performed them at two stress ratios of -1 and 0.1. We got a 50% reduction in terms of fatigue limit between the axial tests and those torsional at the same stress ratio. So this is due to the fact that the torsional loads are more deleterious in case with respect to the axial one. And then we got a 30% reduction in terms of fatigue limit between these two torsional specimens series performed at the stress ratio of -1 and 0.1. From the point of view of fracture surfaces, all the specimens failed due to defects very near to the external surface with a crack oriented onto the maximum tensile stress plane. For the model, we can see in the fractographies below that all the specimens failed from pores very near to the external surface, so they are a spherical shape. If we analyze the stress field around this spherical field, we can see that onto one plane, this defect is loaded in tension and on the other is loaded in compression. From the literature, we know that the ratio between the stress intensity factor in pure tension and in pure shear for this kind of crack emanating from spherical shape is a constant, and it is equal to 0.955 with the stress intensity factor in tension computed with the square root area model. So we adopted a Kitagawa model in terms of stress intensity factor to take into account of this effect, considering also the effect of compressive residual stresses, which were considering into the effective curves shown in solid lines in this slide. As we can see also in this case, the effective curves fit well with the experimental results. For the as-built specimens, we got no reduction in terms of fatigue limit, neither between the axial tests, neither between the two series loaded at the two stress ratio. From the point of view of fracture surface, we got two mechanisms. The first mechanism is triggered by superficial features that produce an initial horizontal crack that then branched in mode 1s. The second one is due to spherical particles that is really the same of the other mechanism found for the machined specimens. So to summarize, we got these two mechanisms between in the as-built specimens. So first initially mode 3 cracks that branch in mode 1, and a fully mode 1 crack starting from spherical defects that in this case are spatters. So we, with this consideration, we found the effective mode 3 stress intensity factor, and then found the corresponding stress intensity factor in mode 1 onto the branch tilted plane with respect to inclined with an angle of 45 degrees with respect to the initial crack plane. Of course, we need to consider that we have to project the residual stress tensor onto the maximum principal stress plane in order to get the effective stress ratio. The stress intensity factor instead for the diagonal oriented defect was computed as in the case of machined specimens. One of the specimen tested at stress ratio of 0.1 was analyzed, and we measured the residual stresses both before and after the test completion onto two positions of the external surface of the specimen as shown on the right. And we found that after the testing, we almost relaxed all the residual stresses. This is due to the fact that at the fatigue limit, for this test performed at 0.1 of stress ratio, the maximum tensile principal stress is very near to the yielding point of the material, and so this induced this relaxation. So as done for the machined specimens, we adopted a Kitagawa model in terms of stress intensity factor, and we compared with the experimental data. As you can see, for the first load ratio of -1, the results are fine with respect to the effective curve, but in the case of tests performed at load ratio of 0.1, not. But the Kitagawa diagram computed for the for the load ratio of 0.1 fit very well with the experimental data, and this is due to the fact that we got a stress residual stresses relaxation. Coming to the conclusions, we shown that for this kind of material, what rules the reduction in fatigue of the fatigue limit between as-built and machined specimens was the presence of tensile residual stresses in as-built material, and not the dimension of the defect that instead is comparable. Machined torsional specimens failed due to cracks emanating from spherical surface defects, and of course the compressive residual stresses that we found are beneficial in terms of fatigue life. As-built torsional specimens instead failed due to two different mechanisms. The first one is an horizontal cracks that branched in mode 1, and from a spherical defect that it was spatters. So the results of this activity are a backbone for a more articulated activity aimed to describe the fatigue strength of additive manufacturing material under multi-axial loading path. I want to acknowledge my colleague from University of Auburn, engineer Patricio Carrion, and Professor Nima Sensei from Auburn University. Finally, I want to also acknowledge BIMIT, an Italian firm that printed out the specimens that we tested in this work. Okay. Thank you.
Thank you, Francesco, for your interesting presentation and work. So now we have, a few minutes, 2 minutes or 3 for some discussion before closing the session. So are any questions from the audience? Well, there are no comments in the chat. Maybe I can start the discussion.
Yes.
Okay, we have a question from Camille. Please go ahead.
I have a question. At the beginning, you mentioned that you want to look at the surface and to look at the roughness of the surface, the influence of the rough surface on the torsional fatigue.
Yes.
Maybe I missed it, but did you measure the roughness on the as-built and machined sample?
No. We only measured the effective square root area due to, let's say, the roughness of the surface that can be treated as an initial defect. So, but we didn't perform any kind of rough measurement of the roughness surface.
Okay, and the machine samples were polished after? Or?
Yes, we mirror polished. So we only have the influence of internal defects. So okay. Pores, mainly pores and sputters due to the machining.
Okay, so the as-built samples are also polished.
What? Sorry.
The as-built samples?
No. They were as-built. So with the.
Okay, so without polishing. So probably you have a difference in roughness between the machined and polished sample and with respect to the as-built samples.
Yes, of course. We have two different roughness, of course. But in this case, in our case, the dimension of the defect that we found were very close between the two series. This is the point.
Okay, thank you.
Okay, you're welcome.
Well, I have one comment or question about the residual stresses. So it was very interesting that measurements you have performed. Can you comment? So the second measurement, it was after failures, right?
This one, no, it was we measured after mid specimen's life.
Okay.
So that is not there were not cracks.
Okay, that's my question was in that direction. Just
okay.
If you have any change in self-equilibrium in residual stress due to the cracking, but okay, you did.
No, it was only a mechanical equilibrium due to plasticization, a local plasticization.
Can you show your data about the as-built specimens where you have shown that there is no difference between this graph?
Yes.
Can you comment this graph because it's for me is not so clear this overlap between
Okay, so for the specimens that we tested axially in at a stress ratio at a load ratio of -1, the effective stress ratio was very near to 0.1 due to the residual stresses that can not vanish due to the loading at a load ratio of -1, and of course also for the torsional specimen that is the residual stresses are still there also after the testing. What we notice is the only relaxation for the specimen that we tested at a load ratio of 0.1. So we were very near to the plasticization, and then we got the relaxation. But if you compare the effective residual stresses of as-built specimen tested at the stress ratio of -1 is almost the same of that one at the 0.1 due to the residual stresses. So this is to show that these three series are cycling at the same stress ratio due to the residual stresses.
Okay.
I don't know if I was clear.
Yeah. According to your opinion, is a question of residual stress is really.
Yes.
Okay. Thank you. Let me see if I have another question in chat. Okay, we don't have any more questions. So I think we have passed the time for this session. So I would like to thank you for participating, and I think Luis could close the session.
Okay. Thank you very much. Okay, so we are coming to the end of the session. I thank you all the speakers and also the audience for your contributions to this session and for the conference also. The next session will start at 2 p.m. And let me thank you again. Good luck for you. With no more delays, we close this session. Good lunch to everyone. See you around.
Bye.
Bye.
Thank you. Bye-bye.
Buenos días, Andrés.